I look forward to hearing what you have to say. I've heard a lot about you, but
yeah, he said the same thing.
But then he went to an office instead. Yes, he said no.
Okay, good morning and welcome everyone to the third last day of our workshop. So it's a pleasure to start the day with Peter Schmelke, who is a professor at the University of Hamburg. Peter started his studies at the University of Heidelberg, as we were just studying, but I was also surprised to find out that he did research work with Julius West on supergravities and supersymmetry also in culture for some time. After getting his PhD from Heidelberg, he went to hold several positions, also in Santa Barbara as a postdoc. He returned to Heidelberg and also held several positions there, including director of the Graduate Academy at Heidelberg, and since 2010 he's a professor in theoretical optics at the University of Hamburg. So it's a pleasure to have him here speak about the quantum simulation and optimization using Rydberg atoms. The floor is yours.
Yeah, thank you very much for the very kind introduction, and in particular many thanks to the organizers and particularly yours for inviting me. It's a great pleasure to be here and hear the diversity of things that are being done locally, but even beyond locally. So I'm really greatly enjoying this. So my topic is kind of different from what has been told about so far. It's about quantum simulation optimization using Rydberg atoms. Now, I do not assume that everybody of you on a daily basis is dealing with Rydberg atoms, so I will tell you a little about in an introductory manner. But as the title already says, there's two parts. The one part is more the physics part. You use the Rydberg atoms as a platform in order to do many-body physics. Yeah? And this is an artificial platform. It's not something which nature holds ready for you, but it's something you can prepare in the lab on basis of ultra-cold quantum gases and basis of recent developments on top of ultra-cold quantum gases. And then the second part is more about an algorithm. Now, this is an algorithm that allows you to solve certain classes of optimization problems. So it's less physics, but of course, this algorithm is designed to be implemented on certain modern quantum computing hardware platforms. One of them is the Rydberg platform, which is in recent days having an enormous slope and coming up and being absolutely competitive with the superconducting or the ion platforms or the photonic ones, which are competitors. Yeah. So this is the table of contents. I will give you a bit of a motivation on Rydberg atoms, largely also giving you the basics about these systems. And then I will go into the first research part, which is interfaces of kind of mixed systems. These are lattices. These are 1D lattices. And the peculiar thing and the novelty is that we have a mix of short-range and long-range interaction in these systems. They are competing, and for that, they give new quantum phases. All of that, and I should mention that, is temperature zero. So it's quantum phases, exactly temperature zero. So that is very well reachable within the realms of modern quantum gases, which I emphasized already. And then, as I told you, the second part is about a quantum algorithm to solve the famous integer programming problem. I will explain what that is, and then on basis of that, it will become a bit of technical, at least in terms of circuitry, but I will tell you our suggestion from the algorithm that would be eligible for, once a fault-tolerant quantum computer is available, to implement it on such a quantum computer in order truly to have an exponential advantage in the performance of the algorithm, of the quantum algorithm, as compared to the best available classical algorithm. And then there will be some short conclusions. So, some facts about Rydberg atoms. Now, first of all, before I start, I should emphasize what experiments can do. We have lasers since many decades. This optical frequency domain can be addressed in the following sense. You have lasers that in the frequency domain 10 to the 15, 10 to the 16 hertz. The bandwidths of these lasers are megahertz or kilohertz. And depending on how much you can invest in terms of money, yeah, they can go down even to millihertz. Yeah. So that means you have almost 15, 20 orders of magnitude of the frequency compared to the bandwidth of the laser. And that allows you to precisely address quantum states even if they are in the midst of a high-level density environment. Yeah. Individually address those, make what people say quantum optics with these, selectively couple states, not one by one only, but dress states with other states, and do this very selectively in the midst of a very messy spectrum, yeah, which is what the Rydberg atoms are. So what are Rydberg atoms? Rydberg atoms are atoms that are highly excited. We all know that atoms have infinitely many bound states. Yeah. So in principle, you have an accumulation of the number of bound states at the threshold, the level density becomes singular, and so forth. But before it becomes singular, there's in between. Take the hydrogen atom, n equal to 1, 2, and now you go where you want to go. So that means the size of the atoms increases with n squared, yeah, principal quantum number, take the hydrogen atom. So if n, if modern laser technology, you can go to n to 10, n to 50, n to 100, n to 200, all very well precisely done and addressed, and occupying only those states you want to occupy. That you have to screen your system from the environment, not to have any disturbing other fields. This is clear, but this is experimentally very well under control. That you have to have very low temperatures, meaning microkelvin or nanokelvin is clear. You don't want to have any Doppler shifts or anything. You also have to trap the system in the ultra-cold environment such that it can work precisely on those systems and not a beam, which doesn't help you. So you really trap these states individually, these atoms individually, and all of that. I will come back to that in a minute. Now about Rydberg physics. The size goes with n squared. That means if n is equal to 100, you have a 10 to the 4 times larger atom than the ground state atom. The ground state atom is an angstrom. If an angstrom-sized object comes together an angstrom-sized object, it interacts, but otherwise not. But we cannot control the physical angstrom, but we can control it on micrometers. Yeah? So that means if this object becomes large enough, then the systems start to interact very strongly. So this is almost the size of a micrometer if n equal 100. Yeah? So this is now the size in terms of atomic units. Atomic unit is 1 Bohr. So you come along with 1,000 factor larger, almost like the thickness of a hair. Yeah? Then if you go up, the energy spacing becomes smaller, 1 over n to the third or 1 over n to the 5, depending on what angular momentum is, generally 1 over n squared. And so the spacing becomes very narrow, and you get lots of states per energy unit. Energy level density is raising correspondingly. Now, all of these are metastable states. Yeah? Yes?
When you say 1 over n to the 6th, you mean as a better approximation to the cubic, or there is no cubic term in the spacing, and then...
Yeah, 1 over n...
the spacing.
The spacing 1 over n to the third would be if you would take hydrogen, right? But 1 over n to the 5 is if you go to the high L states, high angular momentum states, then you get 1 over n to the 5. So then lifetime, if you go up, ground state stable, then you go to excitation, typically nanosecond lifetime. Let's not look at metastable states for some selection where they live longer, but typical states, nanosecond lifetime. If you go up to n equal to 100, lifetime is in the 10 to 100 microseconds. And if you take large L, they are in the millisecond. This is more than enough to do all your experiments. Typically, experiments run in the nanosecond time scale, so you're very well done. And the competing time scale of radiative de-excitation, spontaneous emission is a source of decoherence, no question. And you can even improve on that by using so-called cavities or resonators. But still, this is not something that limits you enormously. But still, you can do many, many operations with these atoms as you do in quantum computing in order to perform your tasks. Now, if it comes, and this is the decisive point for the many-body platform, if it comes to the interaction among the atoms, and you go to n equal 100, and you have to bridge a length scale, say of micrometers, 10 micrometers or 100 micrometers, then what comes to your rescue is that the polarizability of the atom scales with n to the 7. So, compared to the ground state atom, yes?
Finish your.
Yeah, compared to the ground state atom, your polarizability for n equal to 100 will be larger by a factor 10 to the 14. And that bridges large scales. That is kind of what you have if you have, for example, induced dipole-dipole interaction. Yes?
So, what mechanism determines the lifetime?
Spontaneous decay. Emission of photons.
I mean,
yes.
Okay.
And that grows with n to the third. But as I said, you can further suppress it if you put the atom not coupling to vacuum, but coupling to a cavity. The cavity allows only certain modes, and then the lifetime is not restricted by this scale. But extra cavities are experimentally not so easy. Right? Only few experiments have that. Most of them don't have it. Also because it is sufficient not to have it to do what you want to do. So the C6 quantum Hals coefficient goes with n to the. This is a crazy scaling. So you really get, also you have 1 over r to the 6 interaction, the coefficient gets huge. Yeah? And so this is extraordinary properties of Rydberg atoms. Now, there is different types of Rydberg states. Yeah? So there's not just one type, like in hydrogen where you have the O4 symmetry, and everything is degenerate because you have rotational symmetry and Runge-Lenz vector and whatever. No, in normal atoms, like alkali atoms, and these are the workhorses of modern quantum computing in Rydberg physics or modern many-body physics, the alkalis, then you have different types of states. Now, if I want to speak pictorially, if the electron, now this is classic picture, don't take me literally. So if you have electrons circulating around the core, and that would have a high angular momentum, and it wouldn't hit the core, then this would correspond, quantum mechanically speaking, to a high angular momentum state, which is not experienced a so-called quantum defect. The quantum defect is approximately 0. That means it's hydrogen-like. But if you have L equal to 0, it will scatter from the core. The core is complicated. Take rubidium with 50 electrons. It will scatter from a system that is 49 electrons. So that is something which is complicated. It's also difficult ab initio to do the calculation even for that, because the core involves other energy scales than the weakly bound Rydberg electron. So, and that is all encapsulated in a theory that was developed in the past century over the decades, multi-channel quantum defect theory. The defect is this delta n. You see the 1 over n squared reminiscent structure here, which stems from hydrogen type picture, but then there's a deviation, and this is characterized by a so-called quantum defect, which has a smooth dependence on n. So low L states are interdispersed into the spectrum. High L states are reminiscent of the hydrogenic manifolds. Yeah? So this is how you can roughly classify. And what separates low L from high L? Well, if you talk approximately L equal to 0, 1, and 2, this is low L, and L larger than 2 is high L. And here you see the quantum defects and how they decrease if you increase the angular momentum. Now, this is just to give you a glance, how does such a spectrum look like? Go ahead and look at electric field equal to 0. This is here. Yeah? Okay, so we go up. This is a small part of the spectrum. 52, n is 52 is the n, the principal quantum number. D state and S state for 54, a 54p and a 53d, and they are interdispersed due to this quantum defect. But then you see also what I mentioned before, these hydrogenic-like manifolds here, highly degenerate states, which then split if you increase or if you switch on an electric field, and you have a fan of states going linearly or according to the Stark effect linearly, and later on the field becomes stronger also beyond linearity, but we see how this splits up. Yeah? But this is the typical atomic spectrum. To calculate it, you need this quantum defect theory from atomic physics. Yeah? Now, these systems, these atoms, these Rydberg atoms, they interact strongly with 1 over r to the 6th van der Waals neutral systems, van der Waals dipole-dipole interaction, induced dipole-dipole interaction. But it could be also 1 over r to the 3, which is an exchange interaction, a resonant dipole-dipole. For the resonant dipole-dipole, you need to tune a little bit, but that's very well also used experimentally in order to have an even longer range interaction, which behaves as 1 over r to the 3. Yeah? That, as I said, this is resonant dipole-dipole. So these objects, I mean, the Rydberg atoms are very sensitive to fields. You see how these fan splits, and this is not a strong field. This is millivolt per centimeter. Yeah? This is a very weak field. So all these Rydberg atoms are very sensitive to external fields, which is very good. You need weak fields to manipulate them. On the other side, if you have unwanted fields, you have to screen them or you have to compensate for them, right? Because they would disturb your experiment, yeah? And your resolution, your wanted resolution. But principally, this is a toolbox which is used. I mean, the manipulation of the atoms with the fields is a toolbox which it comes to the heart of processing these Rydberg atoms. So now, going from Rydberg atoms now to a little bit towards where we stand. Yeah? Of course, the one thing is you can cool atoms. This is laser cooling, evaporative cooling, and trap atoms. Both are key technologies developed in quantum optics over many past decades, and ultra-cold temperatures. So we are, even if you want to go to Kapodistrian condensate type systems, you go to the nano-Kelvin regime. Otherwise, and most of the experiments which are done for quantum computing are in the low micro-Kelvin temperature regime, where motional effects are very small. You should imagine if you go to 1 micro-Kelvin, your atom is moving at a centimeter per second. Yeah? And quantum effects are dominant. Now, one thing, apart from cooling and trapping, which has become very important over the past 10 to 15 years, now this is, Bose-Einstein condensation was discovered 1995. Now I'm talking about the last 15 years, is an optical tweezer technology, which is essentially what you have. You have a laser, you split the laser with acousto-optical reflectors or spatial light modulators, and you build in space optical foci. Yeah? Here, distributed. Then you load this optical foci with individual atoms, all standard technology. If there's a defect in this loading, you remove it, and you have a perfect 100% loading. This way, you have a setup where confined in individual optical foci and optical trapping, optical dipole traps, there's individual atoms. You can use, yes?
You can put, how many atoms at each foci?
As you want.
Okay.
Roughly as you want. This is all a matter of the loading process.
Okay.
You have a big common trap which has 10 to the 3 atoms or 10 to the 4, and you put either tweezers in and you load, or you overlay and you remove all the rest which is on trap, and you remain with a certain number of atoms in each trap. Okay? So that is all very well under control. But now, and this is just the beginning of it, yeah? You should think what we have now is, if you can make the atoms interact, and that goes through the Rydberg excitation, you have an arbitrary network-like arrangement of atoms loaded in tweezers. It doesn't need to be a regular chain. It doesn't need to be a cubic lattice. It can be 1D, 2D, 3D. It can be any type of, let me call it network, or any type of spatial geometric arrangement. Yeah. So, as I said, there's deterministic loading. You can eliminate defects. And then what people do is, because now you're here, and you're here, say, with two tweezer foci, with loaded with one atom, loaded with another atom. And then you start exciting. If you don't excite, they don't interact. The distance is a micrometer, yeah, or 100 nanometers. This is angstrom-sized object with some motional spreading due to the confinement, which is also by the quantum, because you can cool down to the motional ground state in these tweezers by sideband cooling. And once you're there, yeah, they are not interacting. But then you excite them. And as I told you, this really makes the interaction significant. So you make this, you blow up, you make Rydberg atoms, and then they start interacting, right? Yes.
Within each focus, they do not interact, or?
No, there's only one atom.
That's why I asked you.
Yes.
So you can control only one atom per.
Absolutely.
Yeah.
Absolutely. And this is the aim, because if you would put more atoms into a single focus, you have to worry also about light-assisted processes and other stuff.
Okay.
So we want to remain with one atom at one focus.
Okay, then once you do that, I mean, you know, to actually excite it is a probabilistic process, right?
Yeah, but that, with a given pulse, a pi pulse, you can do 100% probability to go to the excited state.
Okay.
Yes. This is a matter of the pulse. This is another laser, by the way. It's not the same laser that does the tracking. There's optics, if you want to see, have the opportunity to see these optics tables, they are mass. There are many lasers having many different tasks. The nice thing about all these things that they do not interfere is the fact that they are so narrow banded. So the one matches this frequency, the other one matches this frequency, and these all do different tasks to the system. Yeah.
And then you control the end. The exciting
Yes.
level that
Yes.
this is what you do.
Yes. You control the N, you control also the angular momentum, which is in the Rydberg atom. Could be 0, 1, or 2. Yeah? Or it could be, and we are currently collaborating with a group in Kaiserslautern, where you go up to very high angular momentum situations. Yeah. So, but then you have the strong direction. And that's where you want to be. Yeah? And that's where the physics happens. Now the route is open. The route is open to quantum simulation, many body physics with all kinds of 1 over r to the 6, 1 over r to the 3, arbitrary geometry. You can bring the system out of equilibrium. You can do all kinds of things with this. So again, let me emphasize, this is a tunable rearrangement, and you can dynamically also reconfigure your system of tweezer arrays such that, yeah, you have one atom here, you have another atom here, you bring them close together, you entangle them, you bring it away, you take another one, you bring it together, you entangle. You can do it one by one, or if you do it more smartly, like Michel Lupin does it, you take one optical tweezer array, another optical tweezer array of say 1,000 atoms, you overlay them, entangle them, and bring them apart, and they are entangled.
The time scales for this, I mean, you need to do this adiabatically, right? All this.
No, you don't need to. Adiabatically would limit yourself. You can use optimal control. Yeah, so you really optimize the motion, how you overlay it, such that once you go back, you have an optimal for the ground state occupation again. I mean the motional ground state in the tweezer. Because you don't want to have heating in the tweezer.
Yeah, okay.
Yeah, because that would cause the additional decoherence in your system. So this tunable, and then this is why Rydbergs have been coming up so much in the past 10 years. This is a perfect starting point for quantum computing because this is scalable, and as has the last few years shown, fidelities in single and 2 qubit gates are what the ions have, and meanwhile, so this is really going very well. So now this was introduction. I hope it was too much. Now let me start with quantum simulation of many-body quantum phases. So this is the past few years. Negi Seibeck is a PhD student in my group. Rick Mukherjee is a postdoc in my group, but now not anymore. He is building up a quantum technology center in Chattanooga, in Tennessee, in the US now, and these are works from the past few years. So it is about temperature 0, quantum phases of lattices. So the new thing, this has started around 2008-10, where people looked into ground and Rydberg, because this is naturally what you have. You have a ground state, but the ground state is the angstrom-sized non-interacting state, and the Rydberg state, I emphasize, would be strongly interacting. Now we came to the idea, wait a minute, instead of doing this and mapping it to a kind of modified Ising model or this transverse field and driving and so forth, there's one thing you could also do. Instead of looking at these two states, you could prepare experimentally also two Rydberg states, right? And then the interaction would also be about the ground state. Now the ground state is the lower Rydberg state. They would also interact, yeah, instead of the primary state, the true primary state of the atom. So that was the idea. And in this case, you have short and long range interactions. You have 1 over r to the 6 and 1 over r to the 3 if you tune your system. Yeah? And that helps in order to get other, so far unknown, complex many-body random phases, as you shall see in a second. But it is also known from condensed matter physics that this is an interesting setup which enriches the possibilities of different phases in corresponding random phase diagrams. Yeah? So, but in Rydberg, the combination of 1 over r to the 3 and 1 over r to the 6 hasn't been explored. So let me put in a nutshell what we will get up front, so you're prepared to what we're aiming at. Yeah? So we will get some novel random phases due to the competition of the van der Waals and the dipole-dipole. Yeah? So we will look into the uniform chain where the Lagrangian liquid phase can be tuned. That is so far in all existing platforms on the Rydberg side not possible. You'll see here, this is possible, that we can tune this phase. Then I will move to a dimerized chain, and apart from the well-known bond order and the density weight phases in this system, there's a new hybrid type of phase which has both bond order and density weight. That is called BODW. So what is the setup? Now this is the tweezers, okay? This green stuff over here, tell me if I'm saying something wrong because I'm red-green colorblind. Pinpointing. So this green stuff over here is the tweezers, and these indicate the atoms. And this up here is what kind of the schematics of what we have. We go with these atoms to Rydberg states. This is a Rydberg state, this is an arrow diagram, and this is a Rydberg state. Of course, I coupled them with lasers. Yeah. So this is this Rabi frequency type mu W type thing, which. And this laser has a detuning. Detuning is always a relevant parameter in the system. Yeah? It's not always work on resonance. You detune also, which allows you to flexibly change the Hamiltonian. Now this would be an NS. N, remember, is the principal quantum number, and an N prime P state, right? And if you look at this on the right hand side, this would mean I have two types of physical processes, interaction between this atom and this atom. This would be a van der Waals NS-NS interaction. Interaction between this atom and this, this state and this state. This would be an N prime P, N prime P, would be also 1 over r to the 6. And then a resonant photon exchange process. This is N prime P and S and N prime P and S. Yeah. So this is 1 over r to the 3. Yeah. Equal. This 1 over r to the 6 exchange is 1 over r to the 3. That's a resonant process. Yeah. It all comes from Philip-Baker theory. So we have these chains, either this chain, one uniform chain, one-dimensional, constant spacing, or you have a dimerized chain where you have two lengths. That means one length and the second length, and the alpha is just the ratio between A1 and A2. So, yeah, of course, we have this coupling. We have a microwave laser with Rabi frequency omega and detuning, as I mentioned. Now, this is the Hamiltonian, okay? I'm not going to use that one, but this is the Hamiltonian upright. And it is after you have made the rotating wave approximation to the original time-dependent system. So, we have this Rabi frequency, the SP transitions with the sigma matrices, which are projectors, the detuning, which goes to PP. We have PP interaction, 1 over r to the 6, as you know. I and j are the side numbers, so take it for the position. And then there's an SS interaction, 1 over r to the 6. Then there's an SP, which is a 1 over distance to the third power. This is what I told you, what we have in the system. Then there's one thing. If you do a little algebra and go from this, now you could call it spin operators or projection operators. If you go to another representation, an occupation state representation. So you talk about occupation at state n prime p at side I, and that is associated with the presence of a boson at that site. So in this kind of pictorial language, this means the full bullet point is presence of an excitation in the sense of the n prime p, and empty circle means absence of a boson. Yeah? If you formulate your theory within that, you get a mapping to an extended Gaussian-Robert Hamiltonian. It's not the standard Boser-Haber Hamiltonian, that would be boring. We would know the faces of these guys. But here, the deviations from standard Boser-Haber Hamiltonian is that you have a long-range hopping, which comes from the exchange process. This is Tij, which is not just next neighbors. You have longer range interactions, which not just on site, like you have it in the standard Boser-Haber model. And you have a term violating U1 symmetry, so the number of bosons is not conserved, because the boson is an excitation into N prime P. This is nothing which is conserved. Yeah? You have the number of atoms which is conserved, but that's trivial. Yeah? So this is a system where you can have on spot, on Fouquet, only one excitation. It's therefore hardcore constraint. That's what these people talk. And of course the B dagger squared is 0 because you can't have two on site. You can't have two excitations. Yeah. So that causes this Hamiltonian with these peculiarities. So extended, this is the small e as an index. So long range hopping interactions breaking U1 symmetry. So something has to happen if you do that. Yeah. So and here you see what happens. Let's take first the ground state phase diagram for a uniform lattice. We have here the Rabi frequency and here the detuning, and what is shown is SVN, the von Neumann entanglement entropy, by dividing the system in half, taking the density matrix. So the SVN tells you if you here, if it has low values, you're in a regime which is strongly ordered because there's almost no entropy. If you go up, you're in something that has finite entropy. So now let's look into this. So from here to here to here, we increase the T over V. This is hardly readable, 10 to the minus 4, 10 to the minus 3, 10 to the minus 2. And what we see is that we have various phases. There's a phase that is disordered. There is the so-called Z phases. This is just phases, excitation, no excitation, excitation, no excitation. That will be Z2, crystalline phase, and Z3 correspondingly, and Z4 correspondingly, and so forth. So these are crystalline phases. They are density ordered, but otherwise kind of boring. Yeah? But then you see with increasing from the left lower corner, there's something growing up, and this is a large integral phase. That is a non-gap phase. The other phases are gapped. It is power law correlated and carries a certain characteristic. Yeah? So that is a large integral phase, and you can tune the volume of this phase in this sequential phase diagram. As you can see, the domain grows in which the large integral occupies the phase diagram as a function of these relevant parameters. Let's go to the dimerized lattice. So first thing in the this will not be the case, by the way, if you would have not these long range interaction effects. Yeah? Now let's go to the dimerized lattice. Okay, and again, what we have here. We're showing the gap phases here. Don't think about the white stuff. This is non-gap disordered phases. Let's talk about the colored stuff. Yeah, and these correspond to different fractional filling. And again, this is for alpha being not 1. 1 would be the regular previous monomial lattice. Now we have a dimerized lattice. Yeah, and the different colors indicate different fractional fillings. Yeah. So BO indicates bond order and BW indicates density wave. This is pictorially shown here. Density wave again is in a literal sense to be taken occupied, non-occupied, occupied, non-occupied. But this is a quantum state, okay? So this is a crystalline phase. Now if you go here in the bond order, that is the bond order is an expectation value of a hopping operator, which would be non-zero. That's why we have visualized here with a binding between different sides with a fractional filling. So this is a half-filled circle. Yeah? So it's a superposition state which is then occupying the whole dimerized lattice. So this is bond order, this is density wave. They all correspond to fractional 1/2, 1/2 filling. If you go to 1/3 or 1/4 filling, you see these tiny slices here in the phase diagram where you have both bond order density wave in different ways. But you see here, you have a repetition of this, which is the bond order, the density wave type character, and you have also the superposition among these different cells, which actually don't correspond to the unit cell of the system. They go across unit cells. And that is then giving you the bond order but both of them are present, so it's a bond order density wave. Yeah. So, and all of that again is only possible due to the long-range repulsive interaction case, in this case, and long-range interaction. And in this case also, alpha has to be substantial. And all these graphs over here just tell you a little bit more. This is just giving you the corresponding bond order and the density, and the oscillator is expected from these figures. Then you do the structure function, it has the peak at the right momentum, and then you look how the gap emerges, because these are all gap phases, and the gap as a function of V over T rapidly emerges, and then you can compare it and omit some terms in Hamiltonian and try to understand what is truly responsible for this emergence of this phase. Please.
Experimentally, how many atoms can you put in this system? I mean, like.
This is all theory.
I understand, but you know, experimentally,
right.
You can.
Oh, 100.
Okay. So you can.
A few
test,
hundred.
Yeah, so you can test the.
Yes, a few hundred. You might want to do finely sized corrections.
That's fine. Yeah,
fine.
Okay, 100.
Boundary condition dependent. Fine. But if you're in the bulk, in the midst, you get that. Right. 10 minutes. Real or virtual photon?
You didn't see it. You didn't see it.
I didn't see it.
Yeah.
I read it the other way around. Okay.
It's in green, so you can.
Yeah, yeah.
One, yes.
So, yeah.
Zero one.
Okay, so and you can see all of that, and so this is a good starting point, because this was all only 1D. You can go to 2D or 3D lattices. Again, with this kind of competing competitions. You could think about not only having regular periodic lattices, maybe other crystalline configurations, or even aperiodic structures, and you can bring the system out of equilibrium. Of course, you could do quench dynamics, for example, which is the most controllable, and to our personal channel sharing in the community, quench dynamics becomes the most interesting if you quench across phase boundaries. Yeah. Their pattern formation and non-linear equilibrium dynamics is indeed the most interesting. And so, yeah. Okay, so I have the remaining 20 minutes for to show you the second part, which is about the quantum algorithm. Yeah? And this goes back to Cockhill and Rick, but Cockhill did a fantastic job in this. Just amazing. He's a PhD student who really dived into this. So it is about an efficient, I mean really an algorithm that has quantum advantage for solving the integer programming optimization problem. Yeah? So now, apologize, so this is very applied oriented, but indeed the very background motivation comes from this. Yeah? So if you actually locally in the consortium which we have, so-called RIMAX, where they are building locally in Hamburg a Rydberg-based Athens hardware quantum computer, they are really also driven by these kind of applications. Yeah. So logistics operations, where you think about traveling salesman, yeah, or in the more general sense, gradually unconstrained binary optimization problems, spend portfolio, aircraft assignment, feedstock selection. All these are optimization problems practically in industry, and they are classical algorithms who deal with that. Yeah. You can buy them from some software companies. You don't know what they're doing because they don't tell you, and you get on the fly with some results. You don't know, can I do better or not? So, but generally speaking, all these optimization, but many of these optimization problems to solve combinatorial things are NP-hard problems. So they are at least as hard as the hardest polynomial problem. This stands for non-deterministic polynomial hard. Yeah. So the language is a bit of, you have to get used to. So the question which is out there, which is to the whole community, which is not small, is can quantum and quantum-inspired algorithms be an alternative in terms of improving on efficiency of resources and time, right? And yeah, I mean, it's an interplay nowadays, because many of the things that come along are quantum-inspired, because many of the things theoretical physicists have been developing over the years have been applied in theoretical physics, but not much beyond. Now this is changing, because the boundary to informatics and to more applied directions have become fuzzy, to say the least. Yeah. Now, what is the integer programming problem? Well, you optimize a cost function. You want to maximize a cost function, for example. Yeah. And that depends on variables. The variables are, say, discrete. I'm talking about discrete because this is the harder case. If they are smooth and continuous, this is the easier case. Yeah? The hard case if these guys are discrete. Yeah? So you have these xi can take some value, say -1, 0, 1, say something more, whatever you want. But then you have constraints, yeah? And you have a number of constraints, maybe not just one, maybe you have 5, maybe you have 10. In practical cases, you may have the cost function depending on 100 or 1,000 variables, and there might be 50 or 100 constraints. This is not what we can deal with now, but you're trying to deal with this bottom up. Yeah. So this is an NP-hard problem. Yeah. So what the constraints in many cases are not equalities but inequalities. Yeah. So again, if I go from integer programming to continuous variables, it can become linear, non-linear programming, but then it goes from NP-hard to P, and that's not where the challenge is for grand physics. But again, this is continuous variable. We are dealing about discrete variables. So this is just a pictorial representation. Don't take it literally. It's just to visualize things. So I have, say, a C1. It's a constraint, and it's an inequality. So I want all the solutions below this C1 curve. At the same time, I have a constraint which is C2, and I want all the solutions below this curve. Then I have a C3, and I want all the solutions below C3, and this is the boundary. So this is the feasible space. I call it the feasible space. Now, in truly, you have C, or here it is called CF. And that is, once it is in the feasible space, I want to maximize. Okay? So somewhere maybe this is the solution, this one. Okay? This is how I divide up my space into feasible and unfeasible. Right? So now if you think what people have been trying so far, give you a rough picture of that. People started putting the integers into binaries. Okay, that's already an extra effort. If you could directly encode, would be much better. Then the problem of the integer programming becomes, in most cases, a quadratic unconstrained binary optimization problem. But the disadvantage is clear, the scaling. If you have 8 variables and 4 constraints, you read just with this procedure already 250 variables. Wait a minute. So that is quite uneffective. But that's what people have been doing largely in the quantum community for solving these kinds of problems. So there is no direct method available for encoding here. And it's very expensive in resource. So now I'm going to give you a bird's eye view of our algorithm. You have to be a little patient because, as you shall see in a minute, the circuit, which I'm going to try to explain to you, the rough steps, is a little bit of not simple. Yeah. But the main elements you can get. So first of all, we don't use qubits. We use qubits. Qubits have not just 2 states up and down. They have n states. Now you might say, well, this might be an effort how to get it. But if you think about Rydberg levels, and I told you, you can have arbitrarily many states in this given energy window, no problem. Yeah. You have many states available. What you would need maybe is quite a number of lasers in practice to address them, but even that can be helped. So, okay, but then I would need, based on those qubits, I would need to have the constraints implemented. So somehow I need to have a filtering process that separates those states which are the feasible region, because they satisfy the constraints, from the overall space, which might be much larger in Hilbert space, which is the complete space. So I have to separate the feasible from the infeasible, and that's one key step in the circuit which I'm going to be showing you in a second. Then you do amplitude amplification and measurement, and then you project your whole system on the feasible space. And from that point on, you're rid of the inequalities, or rid of the constraints, and you operate only for the optimization of your cost function in the feasible state. Okay? Then, again, I told you, I'm going to use qubits, and each constraint will have a qubit. You're going to see in a second what that means. And then, at the very end, you maximize the cost function, and you do this with quantum operations, this quantum phase estimation, quantum Fourier transform, some rotations, and stuff. Yeah. So everything I'm going to show you in a second has an encoding in terms of quantum circuits. But if I would show you the quantum circuits all in detail, I think on this screen you wouldn't have a resolution there. So, but everything goes back to so simple qubit is 2 qubit gates at the very end. So this is the circuit in its rough bird's eye. Yeah. So we start with n qubits. I told you the n qubits are the variables and their values. Yeah. So each variable is a qubit, and the values of the variables are the subspace in the qubit. Yeah. So then I do a Hadamard gate at the beginning of all these n qubits, and I superimpose them equally. That's what people do to cover algorithmically the state space. But at the same time, I have n qubits. N is the number of constraints. Remember, we have these constraints. So what do I do? After having done this Hadamard, I will make an entanglement. See, this is entangling these space, which is at first place the full space, yeah, with the constrained qubits. Now the qubits will get entangled via a so-called distillation function. Yeah. This distillation function, it's a small circuit, it's really amazingly small, does the job to entangle the feasible states in a controlled manner of the qubit content, namely the one state. So the one state in the qubits would correspond to the feasible states of the qubits, and the 0 would correspond to the not feasible. That's what these guys do. Yeah. So this way, then you end up, after the distillation function has been operating with this unitary transformation, in something that is already kind of has been separated. But the quantum state that emerges at this point has a rather low amplitude for this, or is a mix of this unfeasible and feasible in the entangled manner. But now what I want is I want to enlarge, I want to enhance the part which is feasible. And that is done by a Gruber algorithm, which is standard algorithm or spin flip and diffusion. And that gives you at the very end the absolute dominant amplitude on the feasible subspace on the one state in the qubit. And then you need only a measurement to project. At that point, which is after step 3, we are done with the constraints, because now we have projected the system on the feasible subspace at this point. Now we need to optimize the cost function. For that, we have again 2 registers. This is up here the feasible state space, again along the qubits line. Then we have again L qubits and 1 extra auxiliary qubit. So now what do? We load the cost function as eigenvalues, unitary operations, as phases into these states. This is done with phase estimation and the Fourier transform. Yeah. This is what is this big QPE block over here. Yeah. Then once this is done, this is already put as a piece of information into the phases of these qubits. Then you want to put it from the phases to the amplitude. You want to go to amplitude encoding, because at the very end you want to do a measurement, and the measurement outcome is determined by the amplitude. So what you do is, at that point, you do afterwards, once you have done the Fourier transform and the phase estimation, you do a rotation between these auxiliary qubits. And that brings it as an amplitude to these auxiliary qubits. This is the value of the cost function when it is maximized. Yeah. And that is then finally measured, and then you get automatically projected. This comes from the fact that the amplitudes go inversely with the value of the cost function, and that is imprinted in the phases in the very beginning. So this is how the whole process goes, and let me just show you, because I don't know how much time.
Yeah, okay.
Can I ask another question?
Please.
What's the time needed for this operation?
Yeah, this is this slide.
Okay.
Yeah. This is a comparison. D, remember, was the number of subspace in the qubits. It's D states. And N, of course, is the corresponding number of qubits you need. And absolutely, we have done a corresponding time complexity analysis of this, because we know the circuit, we know the scaling of all the individual elements of the circuit. And this is a table. You don't need to rush through all these details, But our algorithm scales, and this is the decisive point, d to the n half, right? And all other algorithms which are generally available, there are some special cases for special subclasses or problems which work better than that, but they are very restricted in terms of possible setups that they apply to. Generally speaking, the scaling for all other cases is d to the n. So now it's d to the n half. We didn't get it from exponential to not exponential, which is actually a doubtful thing that it could ever happen, but we could get exponential gain, right? And d to the n half is a lot better than d to the n. Yeah. And here's just with problem size some time scaling. Don't worry about the numbers, but you see this is our algorithm here, and these all kinds of other algorithms, how they perform with problem size. Yeah? M is the number of constraints, N is the number of qubits used, and yeah, so this is what the scaling is. So definitely we have some advantage. Of course, this will become relevant once, implementable once we have enough error-corrected, fully error-corrected logic of qubit-based quantum computers, yeah? Which we don't have yet, but things look promising, to my perspective. Yeah. So this is the key elements in view of the lack of time before I get a minus sign. I'm not rushing through this again. But the qubit approach is a key element here. The separation of between the qubit stuff and cost function and the constraints is an idea which might apply to other problems too. Yeah? So the two registers, first Fiesel space, then from the Fiesel space to entanglement, you get back a measurement and you imprint it on the qubit solution space. That's something that could work also for other systems. And so that could be a more general use. But as I said, this is independent of the hardware, whether it's ions or superconducting photonic or Riplet Fiesel platform. There's a natural qubit structure. Although I would like to advertise on the Riplets because for them you have enough as many levels as you want. It might be not as easy to get the qubits beyond a certain number of levels in other platforms, but yeah, that's to be decided. And yeah, I should thank the people which have partly done already. Zeki has been working on the many-body calculation side, and Rick, who is now in Chattanooga, has been working on both sides with us, and Kapil was on the quantum computing, quantum optimization form. And of course, I should thank the local cluster. We have an excellent cluster on Center for Ultra-Fast Imaging in Hamburg, the RIMEX consortium, which is building this hardware, where we're doing also the hardware closed simulations, which I've not shown over here. And with that, I would like to close and thank you for listening.
Thank you for the very exciting talk. Yes, on quantum simulation of the algorithms. Do we have further questions?
Would it be fair to say that you can now simulate whatever quantum spin chain you want, or is it not quite there yet?
In the first part. Yeah,
in the first part.
Well, there's other possibilities still, but this is certainly going beyond the standard quantumizing model. Certainly, yeah. It has a longer range. It has this non-U1 violating term. It has but there's more flexibility than that even.
So, for example, if you want to simulate quantumizing, you would have a spin that can point up or down, but
right.
You now have spins pointing in one direction.
Yeah.
Okay.
Well, you could take more than two levels. Of course, for the experimentalists, hearing me saying this, they shake their heads because they need too many lasers. But in theory, this is all there. Yeah.
And one last quick question. So, if I want to simulate criticality, what would be the analog of temperature here? What parameter would I tune if I wanted to reach a critical point?
Yeah, the parameters are those which I have shown in the case diagrams. You would just need to carefully know where the boundaries are. You would tune your system to the boundaries, yeah. And then, but this is criticality. This is zero temperature again. Yeah. But you would have to probe your system at the boundaries.
Okay.
Yeah. Which is actually an interesting issue.
Thank you.
Thanks for your talk. I have just maybe more general technical question. So I know that you use
Rydberg diatoms for the quantum gate, right?
Yes.
So how is this happening? So just very rough description.
Well, there is the fundamental element of it is two-body interaction, which you do either simultaneously or at a time. So you have atom here. You bring them up with a pi pulse to excited states. You let them interact, and you bring them down with another pi pulse to the ground state, and then the ground states are attacked. But you could do that in many good ways, because the states you select, which you want to be the qubit, could be the ground and excited, the Rydberg state, but it could also be the ground state or other metastable states. Actually, in the platform we have in Hamburg, this is deuterium-based, this is not rubidium-based, this is all rubidium stuff. The deuterium has metastable states, clock states, or so-called atomic clock states, which live for tens of seconds, much longer than any experiment. And then you can entangle these metastable states. It all depends also, these technical aspects also depend what the efficiencies are for the experimentalist to go there fast enough, and how accessibility, and then there's a hell of noise in the system. I'm not even talking a second about noise. Decoherent sources.
So how many atoms do you need for a quantum gate, let's say?
For
a physical one.
Yeah, a 2-qubit gate, 2 atoms.
It's enough.
Yeah. But then, of course, if you want to make a circuit, you need...
No, it's okay, it's a different story.
Two atoms.
So you think that qubits is more easy to construct than qubits?
Well, the future will show.
Right.
There's a certain part of the community who is now moving towards qubits. The reason is that if you have qubits, the depth of your circuit is decreasing. So, the depth of the circuit is the many overlaying qubit operations which you have to do in order to finally achieve your goal. And that depth is complicated, and decoherence limits this depth. In particular, since we have noisy computations at the time being. And decoherence is a real limiting factor. So qubits would allow to reduce this depth.
It's better for the noise.
It's better for the noise, much better. And this is one issue. The second issue, also the encoding is easier with the qubits.
This part of it.
Absolutely. So there's two big advantages, but on the other hand side, for the experimentalists are now used to addressing qubits.
Right.
They would have to develop again. They would have to some parts start again, but some people start doing that now. So I'm not sure if, let's put your question one step ahead.
Okay.
I'm not sure what the final platform with the success would be. I'm not sure.
Okay. Thanks very much.
Very nice comment. Do you have to worry about the fact that the connectivity between your Rydberg atoms, how close they are, in order to do these unitary transformations that you talked about, or?
Yes, you have to worry a lot, but we all know that. You don't want to have the electronic clouds, the Rydbergs, to overlap. If they overlap in the electronic cloud, you have autoionization, because these are with a lot of energy. And autoionization will kick off an electron, and you're decoherent and you're done. So you stay in the asymptotics. Asymptotics means 1/r to the 6th. And no electronic structure exchange process, right? In the asymptotics. But the asymptotics, as you have seen, 1/r to the 6th, C6 can be whatever you want, but stay in the asymptotics.
And the second question is, in order to make this big qubits, you need to manipulate the fields in such a way that you get the degeneracies between multiple. You can have a hop between multiple states locally, right? You need a 3-state system.
Yeah, if you, for example, you would have that readily available in the Rydberg, because imagine you have an L equal to 2, a D state.
Okay, so
you have 5 substates.
Okay.
Many quantum numbers,
Yeah, you have a lot many quantum.
Yeah, but the 1/r to the 6 doesn't break the symmetry.
The N is very big, so
I understand, but don't you have a symmetry breaking?
Propose we move the discussion to the break, which we
Let
will.
him answer the question, okay?
Of course, if you switch on a Zeeman term, which splits these manifolds, you break some symmetry, right? But the sub-manifold states interaction is equally strong.
Okay.
So yes, let's postpone further questions to the break, but I do encourage to come to Peter and continue the discussion. Let's thank me again for the
Start 15 minutes late, right? 10:30.
PDF, right? Somehow it tries to open it in
No, it's according to
yes. Let me try to reach it again because right now but somehow I think maybe I just need to remain PDF because it thinks it's
No, it's PDF.
no, it's fine. It works. So, now as a PDF it should open up. It opens up as PowerPoint.
So the other talks you should do
Yes, even though I renamed it, it thinks it's PDF. But let's go back to the website of the conference. And yeah.
Download it.
Yes, I downloaded before. This is what I did. Let's try to just change. It tries to save it as PPTX. So let me. Yes, so now it should open up as a PDF. Good. It opens still in.
move the file to the.
Good.
Best if it
All right, so it's a pleasure to have Anastasia Valovich from Brown University. Anastasia did her studies at Moscow State University of Lomonosov before coming to the US to get her PhD at Harvard. She held postdoctoral positions at KITT in Santa Barbara, as well as the Institute of Advanced Study, where she returned many times after. And since 2006, she has been at Brown, where she has become a full professor since 2016. You have the floor. Welcome, Anastasia.
Great. Thank you so much, Yorgos. So, first of all, it's fantastic for me to be here. I'm back in 25 years, and that's when I last time came to Greece. So, thank you so much for inviting me. I'm going to tell you a little bit about mathematical structures in scattering amplitudes. There's been a lot of progress in the last 15 or 20 years in this field, so it's impossible to summarize this in a short 30-minute talk, 45-minute talk. So I'm going to just focus on one aspect of mathematical structures, and one-liner summary would be the cluster algebra structure in scattering amplitudes. So if you want one-line summary, that's what I will tell you about. So here's the outline of my talk. I'm going to start with a few introductory motivational slides about the field of scattering amplitudes, why we're interested in computing them and what's been done. Then I'm going to turn my attention on actually what has been done in two particular theories. One is in a maximally supersymmetric Young-Mills theory, and the other one is non-supersymmetric but massless theory. So I'll very quickly just highlight some of the progress, and then I'm going to tell you the actual some of the structures that been developed, and in particular Yorgos worked extensively in this field and made very important prominent contributions. So you probably heard some of that from some of his talks, and then I'll just conclude. Okay, so let me just start with some of the motivations. So if you look at the typical LHC collisions, it looks like a mess of interacting particles. However, the building block, so there are lots of things that go into actual theoretical calculations contributing to these various processes. One of the aspects, the skeletons of these interactions, or the building blocks in these interactions, are the scattering amplitudes. So just normal quantum field theory, scattering amplitudes, and that's what the focus of this talk will be. So we're not going to be talking about the Monte Carlos, PDS, etc., etc. Because to compute the actual cross sections, there are other things you need to know. But for this talk, we just focus on scattering amplitudes. And of course, the standard model has been tested to a very, very high precision at the LHC. But just to summarize, the takeaway message from this slide is that if you compare the error bar in the experimental measurement versus the theoretical measurement, the error bars, it's indicated in gray here, the ratio of theory to experiment. If you see, once you go to 5 particles, so these are the processes, you see this gray area becomes thicker, so the arrow becomes wider, and so it's very important to develop these techniques further. Moreover, if you want exactly to know what is that exactly one wants to compute and to what order, etc., there's a nice Lezouche proceedings where there's a precision wish list, and that's has been updated, I think, every 3 years or so. So that's I just screenshotted some of the processes that I indicated here, and just so I don't save things. You can here's the number 25 April 2025, and you can go and precisely see what's been done and what are exactly the processes that we're looking at. But these slides just serve as a motivation that it's very important to develop the techniques for these calculations. So this is how we motivate just studying these amplitudes. And let me just put it out there. The goals of the whole program is a twofold. So on one hand, we would like to explore the mathematical structures of these amplitudes. So I come from formal high energy theory background as a string theorist, so I mostly explore the mathematics. But on the other hand, we don't want to just do abstract mathematics. We would like to exploit the mathematics that we found and actually be able to compute things that have not been computed before. And I think Zvi Burns summarized it in an amazing way. So the success of this program rests on 2 pillars. So to thrive, one needs support of both pillars. So a lot of people develop those structures, but you really need to, so there's a lot of beauty and symmetry, amazing things been developed, but you don't want to just develop things abstractly. You really want to do the calculations, and it would be even better if the calculations are useful outside our field. So there's been, I will show in the next slide, there's been amazing applications of this program so it started with LHC phenomenology, but the techniques developed went to gravitational wave physics, to classical gravity, to also supergravity, and new formulations of, so some people have been developing new formulations of quantum field theories, it also touches upon various areas in mathematics, such as algebraic geometry, number theory, and of course also important applications, important calculations been done in string theory, and so I'm just going to focus on this little area and tell you a little bit about supersymmetric Yang-Mills theory and UCD. And it's the amplitudes as a field grew enormously in the last 20 years, and in the U.S. we every 5 years a report is usually being made of what the new directions are, where the particle physics is going, so it's called SNOMAS, and now there is a section that's been summarized by Lieber and Jaroslav Trinka, so this is still from 2022, so we'll wait 2027 for the next one, but you can see that this section in amplitudes has a lot of different topics, and again it touches all the way from LHC to cosmology to gravitational wave physics, and it indicates, these are the white papers summarizing important developments in amplitudes and lots of open problems. Okay, and as I said, the community of amplitudeologists, people working on this, grew enormously since 2009, so I started working in this field over 20 years ago, and it started with a small little workshop in Durham with only 50 participants, but now it's, I think the highest so far was at CERN, 400 people, and I think it's still growing. I think I just was at the conference in Munich, and we already planned amplitudes 2030 and 2031. So this was just my motivation for the field. So now I try to show you some actual formulas, and any questions on this? So, yeah, the message is that it's an important field, lots of calculations, so we now, I'll try to sketch a few formulas. Okay, so what are the so let me a little bit more technical. So what are the scattering amplitudes? They're characterized by 4 integers. So we talk about how many particles scatter, so 4, 5, etc. Then we talk about each particle has a helicity, so we call them MHV, NMHV, and squared MHV. And then we have the loop order, tree level, 1 loop, 2 loops. So that's how we're going to categorize the amplitudes. So what's the status? So first, let's look at the integrals. So the ordinary Feynman integrals, summa masses, summa masses, the state of the art for just pure Feynman integrals is 6-point 2-loop integrals. Note exactly, this is really the state of the art of 2024. So the last calculations have been done by Bru and Hen's group, and so the state of the art 2-loop 6-point massless scattering that's been developed over the years. Now, if we look at so that's pure Yang-Mills theory, not supersymmetric. However, if you look at the supersymmetric Yang-Mills theory, things are much better. So the state of the art for 6-point scattering, 6-particle scattering, is 8 loops, and 7-point scattering is 4 loops. And in fact, I'm sure if you're interested, there's a great review again by Yorgos and collaborators, where some of these developments are described. So why is that? So you clearly, there is some value in studying supersymmetric Yang-Mills theory, because as you see, it's not just 2 loops, it's all the way to 8 loops. Well, why is that? That is because, of course, supersymmetric Yang-Mills theory has additional properties, such as supersymmetry, but it has additional symmetry, such as, I'm not going to go in technical description, because each of these words could be lecture by itself, so this is more like give you a flavor of what's going on. So there's dual conformal symmetry, there's Yangian symmetry, and what I will describe to you is a cluster algebra structure. So the simpler, so many of us view this as a simple model that likely can be solved exactly. And in the process of solving this model, we've developed over the years a lot of tools and intuition that has been then been applied to a non-supersymmetric case. And indeed, I will illustrate this in this talk. And this is some of these, again, really developed some of this is one of our white papers for the smell ones. Okay, so let me, these are important huge objects, but let me just try to have a cartoon-like description of them. So we think, so I said each amplitude we index by 3 numbers, number of points, velocity sector, and number of loops. And let's think about these amplitudes just as some complicated functions of some kinematics. So let me just show you some cartoons of what kind of functions these are and what kind of variables these are functions of. So first, what are these amplitudes are functions of? Of course, when we study quantum field theory, we study in the first semester that the amplitudes are functions of momenta in a polarization. Of course, that's not how some of these developments been done, because you start computing, evaluating the amplitudes of the function of polarization, it quickly gets very complicated. So instead, for example, for the supersymmetric theory, again, this is really a cartoon, so instead of thinking about the amplitude as a function of momenta, one introduced some new objects, lines in projective space. These are called z's, and everything is in this functions of z's, so mathematically these are amplitudes are functions of some Grassmannian 4, n, where n is the number of particles. So again, I'm not, this is, as I said, is a cartoon-like thing, and so you describe these amplitudes as functions on some Grassmannian, and what kind of functions are these? So usually the types of functions that these amplitudes are, they are, so the log functions, log x. So more complicated than log x is something called polylog. So these are some polylogs which are recursively, polylog 1 is just log, and then you can define polylog m recursively by this formula. Then you talk about multipolylogs or generalized polylogs, where you deform this formula by some numbers a's. So then there is even more complicated functions. There's something called elliptic polylog. So again, each of these is a lecture course by itself, and moreover, there's also now a sub-community of people doing amplitudes who study just these elliptic polylogs. They have their own annual meetings, etc., etc. So this is just very, very, very. So some of these people, Brodel and others, have been developing these as pure mathematical physics problems. So amplitudes are these transcendental functions on something called Grassmannian. So these are two things. So the other thing I need to say a few words about is that I'm not going to describe the structures that this talk is devoted to. I won't be talking about the whole amplitudes as a function. I'm only going to be talking about the singularities of these functions, and this is something called symbol. Again, let me illustrate that with this example. So, for example, if you take a function log x, its symbol is x. Okay, so I will be so you have a function of some variables. I'll be projecting into certain what are the space in some clever way, well-defined way, into something called a symbol alphabet, which means the singularities of these complicated amplitudes. And this is something we've developed about 15 years ago, and unfortunately I was late to this conference because we just had a meeting in Munich celebrating also reviewing all the developments related to the introduction of the symbol. But again, the takeaway message from this is that I will be focusing on just singularities of these amplitudes. So to give you an idea, for example, if you look at 2-loop 6-point amplitude in supersymmetric Young-Mills theory, and if you start computing it with many pages of this multi-polylog functions, but if you just want to nail down what the final answer is, this is some weight 4 polylog function of some of these particular variables. And in this talk, I'm going to zoom in into what are these arguments, what what is the description of these arguments for a class of amplitudes. And so these are called symbol alphabets, these are called letters or singularities, and so let me just tell you what is known about them for using some examples. So perhaps it's not important, all the notation. So again, as I said, we have loops and legs, and so for example, for two loop, 6 and 7 points alphabet, for example, has been worked out from the amplitude calculations, and there's some known answers for them. And for example, and they're known, and there's the techniques due to, again, Yorgos here and Lance Dixon and collaborators. So people using the knowledge of singularities, you can use something like a bootstrap, where you start with this list of singularities and then impose mathematical and physical conditions, and you can find remarkably unique function, the actual amplitude, which satisfies these constraints. Again, this is Yorgos can teach a class probably on this. It's a amazing work, and they were able to compute this up to 8 and 4 loops. I think this is probably the highest loop ever calculation in quantum field theory. The exact, where you know the exact non-trivial function. So, but the takeaway message from this slide is that it's very important to know these letters, these singularities for these 6 and 7 points, because knowing the set of letters and then imposing physical constraints, you can actually write down your functions and everything about the amplitude up to this very, very high loop number. Again, I'm hiding a lot of extremely technical details in these slides by making these cartoons, but I'm trying to give a flavor of this field, but the expert is in the front row here. Okay, so very good. So this was about supersymmetric theories. Okay, what about? But of course, in real world, you say why you talk about supersymmetric theory. We want to talk about non-supersymmetric theory. So, and again, I showed you progress is of course catching up, and there again, this is more just to give you an idea. So if you look at the two loop 5 and 6 point massless integrals that I already had in the first slide, the letters for these the single so these have been evaluated only recently, especially for 6 points. But the space of singularities is known. So the alphabets that I'm interested in this talk, I could present it for you here. So if you look at the integral, just evaluate this 2 loop 5 point massless integral. The actual singularities are, okay, so here there's lots of brackets, but so these are some invariants. This is a nice compact formula, but again, take away that you can open the paper and this has been worked out. And recently, the important, so now brings me to most recent work, the full set of singularities for this 2 loop 6 point massless scattering arbitrary integral has been worked out. And again, after some notation, which I don't, if you want, you can look at my slides, there are 245 independent letters. So again, I remind you, the integral is some transcendental function of some arguments, and I'm talking about these arguments, and I'm calling these letters. And you can open the papers, and there's a list of letters. And what I'm trying to give you a flavor of is that you kind of looks messy. So what we would like to do is to try to take the answer that's been worked out by brute force hardcore calculation and try to explain is the structure. Can I find some other description of that? Now, why is that important? Because if you're able to understand the structure, maybe you can conjecture the next loop order, next number of particles, etc., etc. So here's so we're going to take this data and going to try to analyze it. That's what we've been doing. So what is the mathematical description of this list? So you saw again. So for 5 points, it's some compact expression like that. But for 6 points, it's again the answer is known. It's this 245 letters. So how do you try to analyze this? Well, this is brings me to the third part of my talk. So I will try to convince you that there's some mathematical object called cluster algebras that I will define for the most simple case that can actually explain these findings from physics. So again, I repeat, physicists computed these integrals for 2 loops, 6 points. They got the set of singularities, this list. Now we want to try to understand it from mathematics. Okay, and for that, let's go back, step back for supersymmetric theory. So this has been known for n equals to 4 Super-Yang-Mills theory for a long time, that these alphabets, that again I'm not drawing, but that they are described by something called cluster algebras. Now let me just have one slide on what cluster algebras are. So cluster algebras is a subfield of mathematics. It even has this mathematical identification number, which is written here. And they play, so they've been invented by Fomin and Zelevinsky in 2000. So this is something 25 years old subject. By now there are classes in many math departments just devoted to this field, but they play a role in a lot of fields of mathematics and topology, geometry, number theory, combinatorics, algebras, etc. And we are just sitting in this little corner. So they also play a role in theoretical physics, not just in scattering amplitudes, but also in conformal field theories and string theory, mirror symmetry. But this is both phases of the part that I will describe, just to give you a bigger picture of what we are talking about. Okay, so let me just, so this is for, let me maybe, let me try to tell you what is the simplest possible cluster algebra. So to define a cluster algebra, you need two things. You need a quiver, which is set of points connected with the line. For simplest case of A2, it's called A2 because it's a Dickian diagram for A2. You have two nodes connected by a line. So nodes, lines. Now, associated to nodes and lines, you have something called mutation rule. And that is fixed by your picture. And that's the formula. There's a defined formula. So you have your variables, two in this case, A1 and A2. And then from each variable, you produce a new variable, a primed one, by this formula. So for example, if you start with A2 and apply this formula literally, you just put like number of variables go from one to another. For the next variable, you get something like 1 plus A2 over A1. And then you continue, you apply it, this is called a mutation. And you apply it to A2, then you apply it to A1, and then you continue. So for this particular quiver, it turns out that this process stops. There are only 5 variables, and these are the variables who are written here. Okay, so this set of variables, A1, A2, A3, A4, A5, is called A2 cluster algebra, and there are 5, only 5, these are called cluster variables, and there are only 5 of them. Now, of course, this gets more complicated, so the best introduction, well, there are many introductions, but I refer if you want to learn more about this, but again, it's a whole class that many departments teach. There's a book by Fomin, Zelevinsky, and Lauren Williams. So this gets more complicated. So for example, the relevant cluster algebra for n equals to 4 Super-Yang-Mills theory is something called GR for n. All that means is that you know a particular quiver that you start with. So here you started with just 2 nodes connected with a line. And here you just, here basically you would know, so when you say GR for n cluster algebra, that means the initial seed is something like 3 times n minus 5, and it's the particular quiver, and the same mutation rule as in the next page. And what you do is you then, similar how you generated these 5 cluster variables, you generate a set of cluster variables from this quiver. So the point is that in math, there is a well-defined process to get these particular variables. So, and as you might have guessed, I'm talking here to you, is if you now take 6 points and look at GR for 6, so from math side, it turns out the quiver that I wrote for general N on the previous slide, it looks like something like this. And then if you mutate and write all your variables, so from mathematics, you start with quiver, mutate, get a list. It turns out that this matches exactly the set of singularities in the amplitude. So that's the connection between the math and physics.
Can I ask something?
Mm-hmm.
The rank of the group is in this A's, the M
Yes.
of SUN, is it in this A?
So this is all for planar. The capital N of SUN, N to infinity.
Okay. So that's what the other remark. So when you say when you say QCD, you mean QCD at large N?
Large N, yes. Mm-hmm. Yeah. I'll come to, yeah. So for now, I'm even before that. There will be also non-planar. There was actually for QCD there was also non-planar. Yeah, there was also non-planar, but I will get to this. For now, for supersymmetric case that I have here, this is planar. So yeah. So okay, so that's the connection. You have these particular class algebra, and you match. So you produce your variables, and that miraculously matches the variables on the amplitude side. Okay, so this has been done. This is quite old work. For 6 and now for 7, you take the quiver, and then that matches. There are new features arising beyond 7. Again, this is the subject of the whole lecture. Yorgos made again prominent, very important contributions there. A lot of work has been done trying to analyze this beyond 7 points. But I want to skip this all and go to Feynman integrals. So now this has been studied for some time again and allowed this very high loop calculations, but we want actually, our goal is to move away from n equals 4 and see what we can do for non-supersymmetric theories. And again, very important paper by Yorgos and Johannes Henn and Dmitry Chicherin, where they observed that it turns out that if you take some integrals, particular 4-point integrals, that the alphabet or the space of singularities for these integrals also could be understood from cluster algebra. So let me just start with this. So these are for 4-point integrals, and so you have again to do two things. You have to compute these integrals, and they've been worked out by Henn and his group to 3 loops. And then in this very, very nice papers, so Yorgos et al. And Alija put here actually, a very, very nice paper, they were able to find this structure for the actual integrals. So, and what they found is that, so I showed you A2, and I showed you what the variables are. So it turns out, remarkably, if you do this for 2 and 3 loops, the algebras are C2 and G2, and these are the corresponding variables. So on one hand, you take the mathematics. So these are well-defined algebras, and you get the alphabet, and then you do a very clever change of variables. This is by these 2 gentlemen here, and then that remarkably matches to the alphabet that Henn et al. Computed by very, very hard calculations. So it's a very, very non-trivial result. That's been known for some time. Now, progress in this field is very slow, I have to say, because somebody has to compute it, takes time, very, deep things, they don't just, it's not a little bad, I should say. So, it took some time, already it's been known, and they generalized it to high loops. But recently, as I mentioned, and this is for 4 points, and for higher points, recently the calculations have been done for 5 and 6 points. So we would like, and those answers are goal. This is again, I'll remind you. Our goal is try to explain this data, this alphabet for 6 points. So I just sketched for you. So you have to be so they knew here for 4 points that there are these particular class algebras. They also been classified. Now, for Yang-Mills, for supersymmetric Yang-Mills theory, we had the something called Grassmannian cluster algebras. But interestingly, there's finite, finite, I actually don't need as much, I will keep them before. So you need a starting point. You need to know what cluster algebra to start with. So coincidentally, there's been also parallel work in mathematics, and something called flag cluster algebras have been developed. They've been developed for some time, but it's been realized that flag cluster algebras could possibly be relevant to the variables that are used in massless scattering in this so-called spinning helicity. So I don't want to go into details. All I want to show you is that similar how you remember I had the A2 and then I had Grassmannian quivers. You play with them, you produce the variables. There's something called flag cluster algebras, and the quiver is I don't know the definitions, I just show you the quiver is known from mathematics. So you take your quiver for the flags, something called flags, you mutate, and you get a set. And remarkably, this matches the alphabet after some work and some permutations. I don't want to go into great detail. Remarkably, that you can reproduce the 5-point alphabet. Okay? So again, I repeat to you one more time. So somebody computed this. So we start with 5 points. So mostly Ken's group computed these integrals, and these are the singularities. And now we apply the mathematics called flag cluster algebras, and we were able to, after some permutations, understand these. Now we want to move to 6. So again, there's a generalization called again would be a whole lecture, just more like a cartoon to give you an idea. A known starting quiver for these, and this is some of our results. So we were able to get all, so there's 245 symbol letters, so most of them we were able to produce. But still some puzzle remains, and still we continue thinking about it. But it's very, very important because, once you have this, then you can start making conjectures and predictions for higher points and higher loops. Okay, so that's again, I tried to start it broad, talk to you about the 25-year-old subject, but now I go to my last papers. But let me just give you some of the outlooks. So again, I really chose tried to explain a little part of it, but there's a lot more has been done. So of course, we've been talking about this set of singularities, just the letters on both sides. So first, there's still a puzzle. We got all out of 245. We still have remaining 36 that we're not that are mysterious. It's important to understand them. Then of course you say, okay, but you talk about just singularities, just letters. What to write the amplitude, you want the full function. So then there's a lot of techniques and from math and physics how to write those functions. And their rules, which letters can appear next to each other, etc. And there's a lot of things have been developed in that area. But instead of going to higher loops, recently we went back down to tree level, and Mark will say in his talk a little bit. So our last paper actually last week was going back to tree level amplitudes, where you don't have those polynomial functions, you just have rational functions, and you can indeed see those new flat cluster algebras appearing. So Mark will say a few words about this. But anyway, so it's important to continue develop. I hope I convinced you that it's important to continue developing this. In particular, it's important to develop, both very hardcore calculations and on the other side mathematics, and make a link between one another, because as I said, the development of these connections allowed the very, very high loop computations in N equals 4. So Yorgos and Lance Dixon and many, many other people were able to go up to 8 loops. So that's why all these structures are very, very important to continue exploring. So I'll just conclude. We've learned a lot. So through these connections to cluster algebras and mathematical structures, and these technologies enabled very high loop computations that previously would have been impossible. So remember, I started with the two-pillar motivation for the field that you don't only just develop the mathematics, but you have to compute something that has not been previously computed. So of course this satisfies this criteria. So new computations have been made possible, which would not have been, which were previously thought to be impossible. And yeah, with the wealth of new data, we anticipate more discoveries lie ahead. So with this, I thank you.
Thank you for the very interesting talk. So do we have questions?
Could you tell us a bit more about the connection of those calculations with the experiment with LHC that you told us in the beginning?
Yeah, okay, so these are just amplitudes. Yeah, so I don't have exactly the slide, but there are people like Thomas German in Munich. So there's a whole community of people who take these amplitudes. We just had a conference in Munich where I don't have the slides, but these amplitudes exactly go to the calculations that are relevant and the progress has been made. Yeah.
Do you compare with the experiment?
No, I don't compare. So the calculation takes many parts. First, you do the amplitude, then you square and compute the cross section. Then somebody else does this. So what we do is just the amplitude, yeah. So some other people do that. Yeah.
So you were saying that I'm non-expert here. So the singularities are the kinematic singularities.
Yes.
But if I want to do something with the experiment, I guess I need the finite terms.
Well, you compute the finite terms, yes. I'm writing some of these integrals diverge. Yes. And there's a known ways to regulate them. Yeah, I'm hiding these details. At the end, it's a finite quantity.
But from your talk, I understood that you have a great handle on the singularity part.
Yeah, but I focused my talk on singularity part. But then, as you saw here, I said that there are also functions. So you have singularities, but you could actually write the exact functions for them as well. But before you do the functions, you need to, I just focused on this particular, on only singularities for this talk. But of course, people, like Yorgos, they write functions. Yeah.
Yeah, a quick question, since I'm not expert. So, assuming that you know the kind of kinematical singularities.
Yeah.
So it's threshold, that's probably Landau singularity.
Yeah, exactly.
Okay. So, if you assume that you know all these things, can you write them down?
The techniques, yes.
So you can do this, right?
Yes, so this is the symbology, this is called symbol. You can write the symbol of this amplitude first, and then you can find the function which gives the symbol. Yeah, that's a two-step process, yeah.
The knowledge of the singularity is enough in order to write down the amplitude?
Yes. I mean, plus, not just the knowledge, plus the physical conditions, like Steinman relations, rigid behavior, collinear limit, many things. So that's how they do this, Yorgos
and this working
they take these singularities,
yes.
Then they make an ansatz. Okay, he can explain to you. His amplitude is the singularities with some coefficients, and then make big linear system, then impose conditions, and amazingly, the system has a unique solution.
Okay.
So it's a highly,
Okay, good.
A few more questions here. Yes.
Okay.
My question relates to the first one. So if this has been developed for planar, in the planar limit, then...
No, planar limit only for n equals 4. I showed you some non-planar.
I mean, this mathematical structure with a cluster algebra. Can you tell us that, for instance, for QC3, non-supersymmetric SU3, are there processes and amplitudes which are precisely similar and they have this cluster algebra as symmetry or...
No, but as you know, to compute the amplitude, you need to first evaluate the integral. So what I showed you is a result for the integral.
So the integrals are similar to those that
the integrals exactly, yeah. Any integral, when you start the real process, this is number one thing you have to start with. Yeah, as you know, everyone knows. Yeah. So, and I showed you precisely the integrals that have these structures. So it's very, very powerful, yeah.
Okay, I'm not an expert, but I would imagine that the existence of these structures, these algebras, would produce some symmetries or some unknown physics, perhaps? Is there a relation? I mean, can you get something about the physical system?
Well, I mean, the Landau singularities have been mentioned. That's similar. They do describe the singularities. Again, the singularities, I don't know if you can do better. Singularities of these amplitudes.
But, I mean, because this is a perturbative approach, right? So
there's also a story which I'm not telling you. There's also a finite coupling story. In fact, Yorgos also participated in this. So it's, what I described is purely perturbative, but there is also a story there, not a different story for any coupling as well. If that's what you are.
well, okay, I was just saying, okay, if I mean you observe a structure, and that structure means some symmetry, and does the symmetry imply something for the actual physics behind?
I don't know. Do you call a computation of an integral which enters in the physics?
No.
I mean,
no, but
I don't know
you have structures.
you have to define for me what you call physics.
I don't know, something about the, some
Perhaps he means if this implies something.
For the theory.
Some hidden symmetry.
This is all indeed for any close to 4 Young's theory. There was a hidden symmetry, which we studied this theory for many years. Dual conformal symmetry. So you go to dual conformal. This was new symmetry found in this. So that's an example. Everything is based on that, for example. Yeah.
And you are saying.
For example, dual conformal. Yeah.
And you are saying because the same structure appears in QCD. There must be some hidden symmetry of
exactly. But again, I mean, I explained some of the structure, but again, there are many puzzles and many developments still to continue. Yeah. For example, another thing remarkable. So there's something called antipodal duality. So Lance Dixon found that if you go, there's these letters. They precipitate a symbol. If you go one way and the other way, they are the same. So that is a miraculous, unexplained property, and nobody understands what the implications are for this theory. So yeah, but again, the final word has not been said. That's why we are working on this. Yes.
Kind of to wrap it up. So philosophically, it sounds like dispersion theory, right? What they were doing in the 50s and 60s.
Yeah, lots of people may connect to Landau singularity. Yeah, the bootstrap, yes, but new important ingredients in this. Sometimes I put even a slide. Variables. They were not using. First of all, they were not studying plane n equals 4, and the variables is they're called momentum twisters. Are very important. So. Yes, it's ideas of bootstrapping and S-matrix. There's a long program, but with modern insight.
And presumably all these cluster algebras didn't exist.
Yeah, of course not, because the cluster algebra relies on this dual conformal symmetry particular. You have to go to a clever variables to see it. Yeah.
Yes, maybe last question, and then we continue with the break after the formal. Yes.
You mentioned this mutation.
Yes.
This mutation rules, who gives this rule?
Definition of cluster algebra. This definition. Yeah. So this mutation rule. It's right here. Once there is a quiver, any number of nodes, and to define, you have nodes and arrows, and the mutation rule is fixed. So, but of course, depending on the nodes and arrows that you produce through it. So it's a defined, very well defined notion to produce your Mr. Singularity. Yeah.
Okay, let's thank Anastasia and both people. And since we have no afternoon session, I propose we take a full break and we resume at 10 to 12. Okay.
Yes, dear friends, could you please sit down? We want to start. They would. Okay, so I think it's time to start. This is the last section of this beautiful workshop, and we start with Olasa Castro Alvarado. She will tell us about integrable quantum field theories for
Thank you very much. I hope you hear me well. I'm going to try and stand here so I can see the slides better. sorry for the people behind me if I don't look at you, but I know you are there. Yeah, it's great to be here. It's great to be in Athens for the first time in my life, actually. So thanks a lot for giving me the chance to speak and to join a very select set of speakers, especially a small and select set of speakers not from Greece. So it's very nice to be here. So there's been a huge variety of topics at this conference. Mine is yet another one. So I'm sorry if for some of you this is really far from what you know. But at least the first 3 or 4 slides I think are understandable and hopefully will give you an idea of what we have been trying to do, even if afterwards it gets a bit technical. So there's been a talk already a couple of days ago by Evangelos about TT bar. So he was taking a much, I would say, kind of comprehensive, broader view of the problem. He gave a very nice introduction. My talk is perhaps a bit more concrete about one very particular problem, but it is connected. But he was talking about classical, I'm talking about quantum, and I'm talking in particular about integral quantum field theory because that's what I really know very well and I've worked on for a long time. So first of all, if by the end of this talk you find this very interesting and want to learn more, there are a lot of papers we wrote about this, quite a few. Essentially what I'm going to summarize today is the PhD project, of my latest student who just defended his thesis a month ago, Fabio. And so over 3 years we worked intensively on these problems, and we wrote quite several papers. I think we have a review that came out even recently that is not here. So there is quite a lot of things, and most of the papers are with Fabio Silis, you see there my students, and my collaborator Stefano Negro. In fact, the people I work with on all these problems are here, so I have a picture. Essentially, Michele, Fabio, and Ricardo, they were all my students at different times. Ishvan used to be a postdoc and has moved on since, and Stefano is a long-term collaborator who's at the University of York. So with all of these nice people, I wrote different sets of papers. So since not everyone here works on integrability, I guess, I wanted to put a couple of slides that are more introductory and that highlight the key properties of integral models, especially integral quantum field theory, which is what I'm talking about today. So integrability is characterized by a number of properties, and well, I think these are the key ones you would recognize if you ever heard of this. So the first one is that these are theories where there are infinitely many conserved quantities. I should actually start by saying that we're talking about 1 + 1 dimensions here, so one space, one time. That's where we find integrability in its natural setting. So we have many conserved quantities. We have, in quantum field theory, the feature that all the scattering processes can be factorized into two-body scattering processes. So we're talking about scattering amplitudes again, as the previous speaker did, but in a setting where everything becomes a lot simpler than what she was talking about. And then there is no particle production in the scattering processes. So what that means is that the two-particle scattering amplitudes are everything you need to fully characterize the scattering theory of an integral quantum field theory, which is very nice and very interesting. Even more interesting is the fact that even though you have all these constraints because of the conserved quantities, you can still have highly non-trivial theories with very interesting physics. So you don't just have trivial solutions, free theories. So here I have a sort of representation of this. In general, you have scattering amplitudes with 4 indices for two-particle scattering. So 2 particles come in, 2 particles go out because there is no production. And you can represent that by an amplitude. And sorry, here I wasn't consistent with my notation. So in one side I put the vacuum state, and I didn't put it there. There should be one. But you have an incoming and outgoing state. And people that do integral PFT will be familiar with this notation. They use these operators are called Samologikov-Fadeev operators that represent the scattering between particles. And because we are in 2 dimensions, the natural variables to use, instead of energy and momentum, people tend to use rapidity variables, which are these thetas here. So energy and momentum are parameterized through these theta variables in a very natural way. And the S matrix, because of relativistic invariance, has to be dependent just on the difference of the rapidities, because under Lorentz boost, rapidities are shifted by a constant. So these are the fundamental objects, and if you are in integral PFT, essentially with some caveats, and it's of course not that simple always, but you can compute them exactly. That's what is special. And I'll say a bit more in a minute. So there is this concept of solvability or exact solvability, which makes integrable models so attractive to so many people. So if we know all the two-particle scattering matrices, we know all the scattering amplitudes, as I just said. But then the two-particle scattering matrices are very severely constrained, essentially because of physical requirements, like unitarity, for instance, and all those conservation laws. But there are so many constraints that, in fact, you can compute the S matrices by solving equations. So you can compute them exactly, non-perturbative. And the program that allows you to do that is often called the S-matrix bootstrap program. So we heard about bootstrap here as well, in a slightly different context, which was conformal blocks in info dimensions. But in 1 + 1 dimensions, we also talk about bootstrap as the program to compute these exact scattering amplitudes. And this is quite an old program going back to the 70s, and the Samological brothers and many other people. Together with this, there is also a complementary part of this program, which is called sometimes also the form factor bootstrap program. Because in integral quantum field theory, not only the scattering amplitudes are constrained, but also the matrix elements of local fields, and these are called form factors. Turns out that a similar thing happens for the form factors. You can write equations for them, and I'll show you the equations in a minute. And if you can solve those equations, you will also know the matrix elements of fields, and from that you can compute correlation functions. So you can actually essentially construct completely the theory. And that's sometimes the way in which these form factors are represented. So it's a matrix element typically between the vacuum, that's the easier ones, although you could have a non-trivial state in there. So you have a local field sitting at the origin, and you have a state of k particles in this example. So you have all these incoming particles, you have interaction with the field, and that gives you a function of all these rapidities with some properties. Okay, so that's the part of integrability. I haven't said anything yet about TT bar, which is really what this is about, but integrability is really the starting point for our program, so I had to say something about this first. So let's now come to the proper introduction, which is the TT bar part. So there are many viewpoints on TT bar. We heard a little bit about that in this conference already, and there's a very large number of publications because people get interested in these perturbations for different reasons. I'm going to give you 3 ideas which were the inspiring ideas for me, because they resonated with me, because they connect with the things I know. But that doesn't mean other approaches are not important, of course. I know a lot of people here are interested in applications to gravity theory, string theory, things like that. Now, one thing that appealed to me when I got interested in this a few years ago is that there is this very famous work that Evangelos also mentioned of Smirnov and Samologikov. And what they said is that if you have an integrable quantum field theory like what I described now, with an S matrix that you know, and you perturb the theory by an irrelevant operator, which we call TT bar, kind of the trace of the energy momentum tensor, or generalizations thereof, so you can have highest inversions of this operator, the theory remains integrable. And that means that you will still have an exact scattering matrix that you can write down. So that's quite a powerful result that holds just in these 1 + 1 dimensions. At the same time, more or less, same year, kind of a few months apart, there was this other paper by Cavaglia, Negro, Cecchini, and Tateo, where they looked at what we call the TVA, the thermodynamic Bethe ansatz of these theories. So there is an approach for integrable models called the Bethe ansatz and the thermodynamic versions of this, which looks at the thermodynamic properties of the theory. So that's something else you can do. And these people did an analysis of those properties using the deformed S matrix you get when you perturb by TT bar. And they discovered that if you do this, you find that in particular the ultraviolet properties of the theory change quite radically because of this TT bar perturbation. Okay, and this is expressed with different words by different people, but sometimes people say that there is a lack of UV completion in these theories. Okay, there is yet another viewpoint that's come quite a bit later, and there are some papers like John Cardian, Benjamin Doyon, and other people, where they connected or they interpreted the TT bar perturbation as having the effect of endowing UV degrees of freedom with a finite length. So essentially, when you perturb by TT bar, you introduce a new coupling in the theory, and this coupling can be interpreted as giving length to particles. And that's why when you go to short distances, when you go on high energies, you go to the UV limit, you start having some problems. So there is, for example, something people call a Hagedorn transition. There is a square root singularity of free energy. So you start finding some very interesting properties, but also unusual and slightly pathological. So when I learned about these things, essentially a few years ago, I saw Stefano Negro giving a talk at KITP, actually in Santa Barbara. I started talking to him, and what appealed to me of all that, and I knew nothing at the time, was that, well, there was an exact S matrix, and if there is an exact S matrix, maybe one can do form factors, which is something I've been doing for a very long time. So I thought, well, the S matrix, yeah, it has this deformation, it's a little bit strange, but people do things with this S matrix, they find some new physics, so could I take this S matrix, put it into the form factor bootstrap program and discover some new things about matrix elements of fields in these deformed fields? That's the basic question. So if all that comes now is a bit more technical, if you don't follow it, doesn't matter. But at least I hope you have an idea of what we were trying to do, at least at this point. So this was pretty naive in the sense that I didn't know about the complications this will have. I just thought, well, let's put the S matrix there and see if we can find some solutions. All right. So that's the starting point. So let me tell you a little bit more. Yeah, your
Maybe we go back to this later, but could you maybe elaborate on this freedom of the finite limit? If it's something we'll say anyways later, it's fine. But that's what I recall, but there was some kind of pathology.
Yes, so I wasn't planning to say a lot more about that later. Not about that specifically. So in a way, these theories are pathological, and that pathology manifests in different places in different ways. So there will be pathologies later, but different ones. More about that, well, as I said, I don't know if I can say a lot more than what I already said, but essentially when you look at the short distance limit, the UV limit, you start seeing new properties. And in particular, this paper is actually quite interesting if you want to look at it, but when they do the thermodynamic Bethe-Ansatz analysis, they start, as I said, they see this so-called Hagedorn transition. So they see that the free energy that you compute from the TVA develops a square root singularity. So suddenly you have two branches, and you can pick one or the other. You have a dependence of everything into this new coupling. So now you have the mass scale, if you are in a massive theory, like I am, and you have this other coupling alpha, and they sort of interact with each other when you study the RG flows, for example. I guess that's, yeah. And then you can interpret this in various different ways. So sometimes people think of this as a change in the metric. So sometimes a deformation of space-time, and that's where the gravity appeal comes from. Other people think, well, there's a finite length of the degrees of freedom, so that's quite appealing if you do string theory. That you preserve instability, that's interesting too. So the point is, yeah, how to deal with these finite length short distances. In the infrared, you normally don't see anything.
May I ask something also? Is the bootstrap program so important in the case of when the systems are integrable?
It is important, it's super important. So essentially, all integral quantum field theory pretty much is built around this bootstrap program. And bootstrap program, I mean, people use the word bootstrap program meaning different things actually as well. So bootstrap program essentially is pretty much any program where you input a thing and you get the same thing back in a way. So it's a recursive way of solving for stuff. But in integral QFT, yeah, the bootstrap program essentially is, yeah, it's the idea that you have so many constraints because you have infinitely many conservation laws that you can actually solve exactly for scattering metrics, matrix elements of fields, and even correlation functions. And the idea, which is something that I think Wyman said, is that if you can actually solve for all of these things in a theory, you fully know the theory. So that's kind of the aim. And since the 70s, people essentially have been trying to do this construction for increasingly complicated theories, in a way. And it's rare, I think there rarely are any theories where everything has been done, because even though it can be done, it's complicated, solve the equations. But you can get pretty far. So that gives you access to very complicated objects in most theories, but non-perturbatively. You have correlation functions, and now nowadays even you can measure those things in experiments. Those integral models are now realizable in experiments. We were hearing a bit in the first talk. So that's kind of the fundamental way in which integral QFT has been studied since the beginning. Yeah. And I think that's actually sort of the original bootstrap program. So at some point people believed you could study all QFT in this way, but then it turns out that for 1 + 1 dimensions is particularly strong because it's enough to fix everything. Any more? Okay, so that's, as I said, sort of end of the introduction. So let me say a little bit about TT-bar. Let's see how far we get. So I told you that Smirnov Samolodikov discovered that you could perturb by TT-bar and preserve integrability. They made this a little bit more concrete. So they actually said that, more precisely, the scattering metric can still be computed exactly. And actually what happens is that it is the same you started with, but it's deformed by a factor. And this factor is usually called a CDD factor from Castillejo, Dailis, and Dyson. So the CDD factor, in general, is a function you can multiply the S matrix by without changing its fundamental properties. So essentially, you have a solution to the bootstrap program. You can construct a new one by multiplying by this factor. So that's actually one of the caveats of the program, that the solutions are not unique. So you often need some additional knowledge about the theory to fully fix the S matrix. Now, the CDD factor that they found is a function that looks like this. And here, because I don't have time to do kind of details, I'm thinking of a theory that has a single particle in the spectrum. So the S matrix now doesn't have any indices because we just have one particle. So you just have same particle comes in, same particle goes out. You could think of a free fermion, then S is -1, free boson +1, Sinch-Gordon model, some very simple hyperbolic function. We will see that later. So if this is your original S matrix, and now you perturb by TT-bar, you get a new S matrix, which now depends on some new parameters alpha, and this is the factor. This is the CDD factor. And if you only have one term in the sum for S = 1, that is what people typically call TT-bar perturbation. But you can have others with other values of S in there, and this is called generalized TT-bar perturbations, with high-spin versions of TT-bar. So the set of S in the sum typically are drawn from the set of spins of the conserved quantities in the theory. And which spins are present is actually theory dependent. So it depends which module you started from. If you have a single particle in the spectrum, like in this example, usually you will only have the odd spins present, because you need this to ensure that the CDD factor satisfies crossing and unitarity, which are fundamental properties. But in more complicated theories, you can have other S present. So the function, the change, seems pretty simple. It's just exponential of Sinches, but this is a highly oscillatory function. The Sinch theta gets very large, for theta large, and p theta to -infinity. So the asymptotics of the S matrix is changed. And actually, most S matrices of principal QFT, they tend to a constant when theta goes to infinity. So now we have this factor that, so that is no longer the case. And that is kind of, in a way, to blame for all these pathologies we talked about, is one way to see it. Here's a picture of this sort of finite length idea. So this comes from this paper of Cardi and Doyon, where they gave this interpretation. And this is a nice way, pictorial way to represent it. So you have kind of a 3-body scattering process that split into 3 2-body scattering processes. And if you perturb by TT-bar, you still have the integrability, so you still have a sort of, you could write a Yang-Baxter equation, if you're familiar with that, but all the lines are thickened in some way. And actually the thickness will depend on the particle type, if there are several. Okay, so that's the change that we have. So now S depends on this alpha, and alpha are those new parameters. And now we come to the full factor program, which is what we were trying to do at the very beginning. That was the original idea. So as I told you, it is known since the 70s that the matrix elements of local fields in an integral QFT satisfy some equations, satisfy a bootstrap program. These are the matrix elements. If I take this S matrix from the previous slide as input, they will now depend on these alphas as well. And the equations that they satisfy, the 3 basic ones are these. Sometimes there are more if they are bound states, but just keep it simple for now. They are complicated enough. They won't appear again because from now on I'm just going to talk about the simplest case. But just to give you an idea, you typically have 2 equations, Watson's equations, which tells you about the sort of monodromy of these functions as functions of rapidity. So what happens if you exchange 2 rapidities? What happens if you shift by 2 pi I. So the first equation is a consequence of the scattering, simply. You exchange two rapidities, you get an S matrix. Second equation is usually called crossing. So you take a particle on a trip around the world, goes to the end of the list here, the theta. And the third equation is called kinematic residue equation. So it tells you that if a particle and antiparticle are present, they annihilate, and there's a pole. There should be a pole on this matrix element, and the residue of this pole is related to the form factor with two less particles. And actually this equation is, well, they're all important, but this one is the one that allows you to solve for any n, if you are lucky. So you can solve recursively. So you start with 0 particles, you get 2, and then from 2 you get 4, and so on. Yes?
Is it easy to explain why the pole is first, or the simple pole?
Why is it first order? No. So, I mean, I don't know. I mean, I can explain the factor here, so you have somehow two contributions, so you can sort of first annihilate the particles, and you get just the rescue I, or you can make them scatter with everyone else, come from the other side and annihilate. So that gives you these two contributions with the minus in front. Why is that only order 1? I don't know the fundamental reason. So I know that if the scattering theory is quite complicated, you can have higher order poles. But these are not of this type. They are not at I pi. They are not kinematic. So the kinematic is always first order. But you can have bound state poles which are more complicated. Yeah. Okay. Other things? All right. So these are the equations, and the naive question I was asking is, if I plug in this deformed S matrix here, can I still solve them for some theory? Okay. So we took this and we ran with it. So how do you actually solve this equation? So this is a very old program, so there is a very well-established set of steps how to do this. Again, going back to the 70s and also the 90s, Smirnov did a lot of work on this, especially on solving this kinematic residue equation. But the basic idea is that you normally start by finding one function, which is called this minimal form factor. So, and this minimal form factor is a minimal solution in the sense that it has no poles. So you forget about this kinematic pole for now. You can deal with this later. So you look at the first two equations, and you try to find a function with good properties. Okay, I will explain what that is. That satisfies this equation. And actually, because of relativistic invariance, if your field is spinless, okay, so remember this is for talking about form factors of a field. If the field is spinless, you can also argue that this function does not depend on two rapidities separately, depends only on the difference. So in fact, the two particle form factor depends on one rapidity variable and then those couplings, if they are there. And you have these equations. Essentially, what happens if you change the sign of rapidity, what happens if you shift by 2 pi I. So that's where you start from. And there is a prescription to solve an equation of this type, which is known for a very long time. And it goes back to Kapodistrian already. And essentially what Kapodistrian showed is that if you actually have an integral representation for the S matrix, or in other words, if you actually have a Fourier transform for the logarithm of the S matrix that is well defined. Okay, so that's an important property. So this G here is the Fourier transform of the log of S, essentially. So if such a thing exists, and you can write S like this, then it's actually very easy to prove that the minimal form factor that solves that thing there, it's gonna be like that. So it's the same function G that is there will appear here. And that's, it's an easy thing to compute. You just plug it in and see that it works. So this is what works for the undeformed S matrix. Okay, that's what people always do. Now, so what can we do with the deformation? So you remember that the deformation of S was by a multiplicative factor. So that means that essentially everything factorizes in this equation. And so the natural thing is that the new minimal form factor is going to be the old one without deformation times a function that we need to find. And that function itself is going to satisfy this equation where instead of the S matrix, we now have the CD factor I wrote earlier, this exponential of change. Okay? So essentially the new equation to solve ends up being this equation here. Now this CD factor was pretty simple. function. So this equation is actually not that hard to solve, although it took me a while to spot it, but eventually you find the solution. And the solution actually looks like this for this function. So you end up with two pieces, essentially. There is one piece which is essential to solve the equations, and that's this function here, phi. And you see that there is one part of the function that looks very much like the CDD factor itself. So you have sum of singes there, again, in all the couplets. And then there is another function, which I call C in here, which is totally arbitrary in a sense, except for the fact that it has to be an odd function of this, so it has to be invariant when theta goes to minus theta, and it's also, so it has to be quotient in there. But the s's that appear in there and the couplings, a priori they are arbitrary. So whatever combination of quotients you put in here, you will satisfy the equation, essentially. So that's what we found in our first paper that we wrote on this. And, well, there are some observations to make. I mean, the first one is that there seems to be a lot of freedom here for all these betas. And that is unexpected and quite unnatural, because when you do form factors for standard theories, typically the minimum form factor is totally fixed, and there is no arbitrariness in there. Whereas here it looks like we have a million solutions. So which one is the physical one? How do you make a choice? In a sense, it's as if the minimal form factor now has its own CDD factors, its own arbitrariness that appears in there. So the first question that emerged at the beginning of this program was what is the role of these parameters? Can we fix them unambiguously? We didn't know the answer to that, and so we did the lazy thing in a way, which is we said, okay, let's take them all to zero, which is the simplest solution, and see if we can actually find some correlation functions, some solutions by taking this minimal form factor deformed by this function phi, and just by that function there. Okay? So that's what we did, and essentially with this idea we wrote 3 papers where we looked at a particular model, the Ising model, which is the simplest. We found some solutions, and general solutions even for any particle number from these. We looked at correlation functions, we looked at their behavior, and we had some nice results that we could interpret, but we were still not that satisfied with the way we fixed these betas, which was really not justified. It was just the simplest solution. So then we tried to find ways to fix this. We spent 2 years, my students worked very hard on this, I must say, trying to do perturbation theory, various things to find a way to explain these betas. And then kind of in the last year, we figured it out somehow. So we found a way that's at least quite natural to construct these parameters and to fix them. So I'm going to tell you a little bit about that as fast as I can go. Let's see. So how did we do that? Well, the first step for us to understand that was to have a closer look at these CDD factors and to understand them in a more general context. So that was the equation I showed you at the start, the first equation. So that's the CDD factor in there. Now, when I started working on integrability, a long time ago, very long time ago, 27 years maybe. So I also learned about CDD factors, because that's something you learn when you look at scattering theory. So there's always this statement that in integral field theory you can fix the S matrix up to CDD factors. But normally when you learn CDD factors from reviews on integrability and so on, what the CDD factor looks like is a function like this, pretty much. So you have some hyperbolic function, and if you look at a function like this, you see that S of theta, S of minus theta is 1, so it satisfies unitarity automatically. So if you multiply any S matrix by this, unitarity is still satisfied. It also satisfies crossing. So if you do S of theta, it's the same as S of I pi minus theta. So you find that any function of this type is a good CDD factor. So the question is, are these two things fundamentally different from each other, or are they related in some way? And of course the answer is that they are related, they're not fundamentally different, and in fact you can turn this function here into a function like this, and it's not too complicated to do. Now interestingly, this function here is not just a CDD factor, it is also the S matrix of a very famous theory, which is called the Singe-Gordon model. And I don't know if everyone here is familiar with that, but the Singe-Gordon theory is usually described as the simplest interacting integral quantum field theory, because it has single particle, no bound state, yet has a non-trivial S matrix. And this capital B here is the complement of the Singe-Gordon theory. which can take values between 0 and 2. So this is a very well-studied model. So if you take this as matrix and you do just something very, very simple, you do the logarithmic derivative of the S matrix. Here we put this little b, which is capital B plus 1, just to make the formulas a bit nicer. You take that function, you expand these functions for small theta in powers of exponential of theta, and you get an expansion like this. If you symmetrize in theta, you get that kind of expansion. You can do this with mathematics, it's very simple. Then you can just integrate this back, and you get a formula like this. Well, this is a formal expansion, so it's not convergent, it's not nice, but it's a simple way to relate the CD factor to the kind of TT bar CD factors we were talking about. And what do we see? Well, we see these hinges, they are there. Only odd spins are present, and this is also what you would expect for Sinch-Gordon. And you have some coefficients, except that now there are no alphas because the coefficients are totally fixed by the theory, so they depend on the coupling. There is a minus outside, and this comes from fixing the integration constant. And it's easy to fix because we know that S of 0 should be minus 1. So the way to ensure that is to put a minus in there. Now minus 1 is also the S matrix of the Ising model. And that means that if you look at this now, you can say that the Sinch-Gordon S matrix, you could think of it as the Ising model perturbed by infinitely many irrelevant perturbations, but with very carefully chosen coefficients. Okay, so these alphas are fixed to very precise values so that we can actually flow from Ising to Sinch-Gordon. So this is a quite nice picture. So here is everything I said is written here once more. This is just a picture. Capital B was the coupling of Sinch-Gordon. It's just a number between 0 and 2. And then we use little b, which is related to it. Yeah. So this theory has a coupling. Yeah. So here's a picture of these coefficients that we found. So you see that there are oscillatory functions, positive and negative. I mean, they are carefully chosen so that these, they're particular of the model. This viewpoint where somehow you can take a non-trivial, take a theory and sort of guide the RG flow to another integral theory in some way by choosing the right type of perturbation. This is actually a viewpoint that some people have thought about quite a lot, and there are papers by André Leclerc and Changbin Ang from 21, 22, maybe more recently even, where they exploit this line of thought, except that they use this to try and find some integral models somehow. So they say, okay, starting here, if I use this perturbation, are there any combinations that bring me to a place that is UV complete? Okay, so that's another way to pursue this idea. But okay, I will say more about that. Now, why is this exercise useful for us? Well, for us it was interesting. We wrote a paper about this because once you realize that the S matrix of a sort of normal theory, UV complete theory, no problem at all, can be written in a TT bar form, then you also know that the minimal form factor of a normal theory must have a sort of TT bar representation. And so that might be a way to understand what these betas are that we couldn't fix at the start. Because in Sinch-Gordon, they will be completely fixed. So what is the minimal form factor in Sinch-Gordon? So this is this function. Again, this is a function people have known for ages. It's very famous from this paper here, but actually people knew it much earlier from Sine-Gordon already from the 70s. Everything was done in the 70s in integrability, and mostly by Samological, everything. It's a function people use a lot to do numerics, to compute correlation functions. And in this formula, actually, this curly theta, I didn't write it, forgot. Curly theta is I pi minus theta, where theta is not infinity. Okay. So if my observation is useful, then what we should be able to prove is that the minimal form factor, this minimal form factor that we know already in this representation, should have another representation where it is the minimal form factor of Ising, so the unperturbed theory, times one piece, which is this function I was calling phi, which was e to the I pi minus theta over 2 pi times the sum of all these Sinches. So essentially, in this case, the Sinch-Gordon S matrix with a minus inside the log. The CD factor will be there. And then there will be this function C, and this was the function that all these betas I didn't know how to fix. But in here, there are no betas. So these betas must be some functions of the coupling as well. what we set ourselves to do was to find this representation. And we actually did. So we found such a representation, so it all makes sense. And here's the formula. So how long do I have now? 5 minutes, probably? Okay. So,
5 minutes.
yeah. Okay, so I'll try and go quick. But, so this, okay, for some of you here, this is not scary at all. I've seen bigger formulas in this conference. But, okay, there are a few terms in there. Let me just tell you what is important somehow. So this is actually the log of the minimal form factor in this formula. There is a piece here which is the log of the form factor biasing, so that's what we expected. There is a constant which fixes the asymptotics. And the piece that is also important here is the bit that depends on the CD factor. So it's also in there. You get that. But then you have all of the rest, and here we have some polylogs we heard about previous talk, logarithms and so on. And all of these functions all put together would correspond to that function I was calling C in my general formula, which was exponential of sum of coches. Okay, you can write that in that representation. So that would be the function that has all the unknowns, except that in Sinch-Gordon there are no unknowns. It's a function of the coupling, like everything else. So why is this function there? And how do you fix that? In a sense, what I'm saying is that if I didn't have all these red pieces here, what is left would solve the equations, would actually be a solution to the equations. And yet, people somehow insist on having all this other stuff present in the representation. So how do you fix that? Well, essentially, there are some requirements that are important, and essentially this function is what you need to fix those requirements. And in the case of Sinch-Gordon and most integral PFTs, what you want to have is analyticity. That's a very important part of the program. And in fact, here you have logs in many places, so you have to be careful. The presence of those additional logs and polylogs allows you to get rid of all branch caps or branch points in this formula. You can show that. But also, this formula has constant asymptotics. And a nice asymptotics is also an important part of the program because these functions are part of the form factors. The form factors go into correlation functions. You often want to integrate, so you want things that don't diverge, don't have strange properties. So, yeah, requirements of analyticity and asymptotics allow you to fix this. Okay. So if you have PTY perturbations, can you kind of put these to use in some way? You can, okay, and in the end we kind of managed to find a way to write things that, it's a formula that interpolates between this that we found here and the PTY perturbation. So the main difference now between Sinch-Gordon and a PTY perturbation is that in Sinch-Gordon you have infinitely many of those. And so how they add up to create something that is very nicely behaved. If you just perturb by TTY, you only have one of these Sinches. So yeah, it's a quite different function, but can you construct a minimal form factor that would be a formula that's valid for both cases in a way, once you fix the coupling? This is what we managed to do, and actually in the end the solution was pretty simple. So I'm going back to this integral representation, rushing a bit at the end. So we've seen this formula earlier for the minimal form factor. We saw the particular formula for Sinch-Gordon, which is some particular G in there. Now there's another way to write this formula, which is this. It's easy to get here. Remember that this G is the Fourier transform of the log of S. So if you use that inside the formula, you can also write things in terms of the log of S. Okay, so this is a calculation that all of you can do if you want to. So you end up with this, and then you have the S explicitly in there. And then you can say, okay, so why couldn't I use this formula to deal with the PTY perturbation? So I just have to put the S matrix in there and run with this. Well, the problem with the PTY perturbation is that this CDD factor, although it's very simple, it's just exponential of sum of Sinches, it is just the kind of function that doesn't have a well-defined Fourier transform. That's why you have problems when you try to do this. And this is easy to see, actually, if you just take the Sinch. So if you just take the CD part of the S matrix and you put it in the formula, you end up with a formula like this, with the Sinch, I have to find, yeah, okay. If you try to compute that integral, you see that it diverges, okay? You can see that it diverges in various ways. One way is to expand the whole function like this and then integrate in T. You see that the T-dependent part is essentially the Laplace transform of Sinch. And this Laplace transform is only defined for some values of this m, whereas we want sum for all m. That's where the problems arise. So the way that we managed to fix this was to essentially subtract that similarity from the sum. And what it amounts to in the end really is to replace this sinh by an exponential. It seems very crude, but it turns out that that works, and that reproduces also the sinh-Gordon representation. So that works for Tt bar, that works for sinh-Gordon. So I'll finish. I'll just show you the kind of formula you get for Tt bar. So you have the phi function there, the basic solution we had, and then there is a dressing by some complicated function in there. And although this doesn't look maybe particularly nice, it is nice. It has nice asymptotics, it's analytic, it has all the properties that you want. And if you have infinitely many of these alphas for the correct values, you get sinh-Gordon as well. Okay. So I'll just go to the conclusion. Sorry about that. I won't discuss this bit, it doesn't matter. But let me conclude here, since I went over time. So in summary, we propose a program to compute the building blocks of correlation functions, m form factors, and here is perturbed by Tt bar. Along the way, trying to understand things, we found this new representation for the minimal form factors. And I should say that this was actually quite a surprise for us, for me in particular, because I worked on this for a long time. These form factor representations have been known for nearly 50 years, this formula, and yet somehow we managed to write it in a different way, which is actually numerically very efficient, more than the presentations people have used so far. So that was already an interesting follow-up of this. So we have been able to fix this minimal form factor, which is the basic starting point for the whole program. So we are really still at the very beginning of achieving what we set out to achieve. But the construction of higher particle form factors is not yet fully understood, in the sense that if you now plug this into the equations and try to solve, they are not easy to solve. And in fact, we're not even sure these are correct equations anymore. So we're a bit of an existential crisis at the moment. So it's better to stop here. But yeah, thank you very much.
So you mentioned this generalized back deformation. So what does they exactly?
So generalized, it just means that, well, if you think of it in terms of the fields instead of in terms of the Tt bar operator, let's say. So this is Tt bar really is an abbreviation of the trace of the stress limit tensor. So in CFT, that is exactly T times T bar, holomorphic times anti-holomorphic. If you have a mass, like in this case, there's a piece which is also the trace that is involved, the trace of stress limit tensor. So that is a particular field which is irrelevant in terms of its dimension. But if you start doing derivatives of that field, you can construct a tau of higher spin fields, which are also irrelevant for the same reason.
But can you express everything in terms of the stress tensor?
I think so, yes. I think you can construct these fields in terms of the stress tensor.
But the way you did it is not in terms of the stress tensor.
Well, I didn't use that kind of language because I worked just with the S matrix. And essentially, in this CT factor deformation of the S matrix, the way these higher spin fields manifest is by having more singes. So you have sum over sinh S theta, and the S is the spin of the field. So in a way, the details of the combinations of fields that contribute, which is the structure of the conserved charges of the field, in a way, we don't use that. That is complicated, and actually it's not even known in all cases what these charges look like. We just know they will be related to stress and tensor in some way. Yes?
A couple of transparencies before the end. You
Yeah.
regularized an infinite
Yes.
divergent
Yeah.
integral. What was the guiding principle? Is it unique, or maybe you can comment on that?
Yeah, I mean, so is it unique? The way of doing it, probably not. There might be other ways to regularize. There might be other ways to modify this that would still give you a convergent integral. I'm sure there are. But this seemed natural.
But would you end up with the same result?
That I don't know. So we didn't try other ways. We just, this somehow seemed to jump at us as a very natural thing to do. Because when you do the computation in this way, essentially you do this Laplace transform, you get this formula, and you see that it doesn't work for m equals 1, but you can just subtract the m equals 1 singularity, and then it's fine. And that is a procedure you can generalize easily for higher speed. So this seemed to be the natural way to do it, probably not the only one. The way we became convinced that was also a correct way to do it is that we could recover representations we know in other ways, for example, singe coordinates. So we knew that this seemed to give the right result. But there are probably other ways to regularize that interval. I don't know. I mean, it seems natural. In the end, the problem is that you have these two exponentials. You're just getting rid of one of them, literally. That's what you're doing. Replacing singe by exponential t. Yeah.
Yes, the last question.
TVA. So TVA was done early on, so I already mentioned Stefano. And they have done actually many follow-ups from that. So there's quite a lot of work on TVA looking at different things. Beta ansatz, not too much. There is something on beta ansatz, however, so there's some interesting work by Potsgai from the Hungarian group where they try I think they do XXZ. So there is some papers about that, trying to understand what this T2 bar deformation looks like on a chain.
Beta ansatz fixes the CDT, that's why I'm asking. If you do beta ansatz,
yeah, also
rigorously done.
Yeah.
This fixes the CDT. So
Okay. Is that a viewpoint people have used? I mean, I'm actually not sure now. I think it could even be that the paper of Stefano, I should know this, but that the paper of Stefano and collaborators actually did this on the TVA because it was pretty much simultaneous with Smirnov and Samologikov, and they also get these deformations. Probably that's how they did it. Yes.
Pero can we postpone it for after? Because we are out of time. Thank you very much.
Thank you. My point. It was
Thank you very much. Very good. It works. Okay, so let's move on to the last speaker of the conference and of this section. It's Mark Stradlin from Brown, that he will talk us about amplitude zigzags.
Okay, thank you very much. Thank you also for the invitation. It's a great pleasure to be here. I'm very sorry to keep you from your lunch. As you'll see, my talk will be, I'll just try to keep you entertained. My talk is about amplitudes, and Anastasia gave a lovely talk that explains the motivation for a lot of what we do. There's a joke that when you give a talk, the first third should be understandable by everybody, the middle third should be understandable by experts, and the last third should be understandable by no one. And if you consider my talk with Anastasia like mine is a continuation of her talk, then basically all of my talk will be understandable by no one. That's what I fear.
That includes including the speaker.
Yeah, of course. Most importantly, the speaker. Okay, so I won't spend much time on the motivation. In recent years, we've seen remarkable progress, and the progress has, on the one hand, we've uncovered beautiful mathematical structures, and on the other hand, we've learned a lot about amplitudes that have had direct impact on actual LHC data analysis. So my talk will have two short pieces. One is some recent developments on tree-level amplitudes for gluons, and this part actually was inspired by one of Yorgos's papers, but it's based on a couple of papers we wrote this year. It involves something called zigzag diagrams that I'll review. And the second part of my talk is some recent work we did following up on a new formalism by Nima Arkhani-Hamed and collaborators that involves something he calls curve integrals. So really, my talk will be very non-technical, and I just try to give you a cartoon of what these things are and why we find them interesting. My talk, a fair criticism you might make about my talk is that it will be very heavy on formalism. So Anastasia emphasized the connection to experiment, and my talk will more emphasize the theoretical or philosophical aspects. Now, sometimes, very rarely maybe, but sometimes it does happen that when you develop a new formalism for physics, you can learn new physics. So the example we sometimes give is Lagrangian mechanics, right? Lagrangian mechanics is equivalent to Newtonian mechanics, but once you have Lagrangian mechanics, you can see how to write a path integral, and then you can move to quantum mechanics. It's harder to see how you would move from Newtonian mechanics directly to quantum mechanics. So a new formalism helps. But sometimes new formalism doesn't teach you new physics, but it's just useful for understanding physics you already have. Okay, so now let's move on to part one of my talk. And this will be about tree-level scattering amplitudes of gluons. Gluons are self-interacting spin-1 massless particles. They're part of the main constituents of matter, protons and neutrons. They're fundamental particles that are scattered by the billions at the LHC, so it's important to understand them. And because they're spin-1 particles, massless, they come in two polarization states, left and right circular polarization. So let's consider the question, what is the complexity of computing this tree-level scattering amplitude where you have a certain number of positive helicity gluons and a certain number of negative helicity gluons? Now, I'll go ahead and give a spoiler. This will play an important role in a few slides. We know the answer is at worst order n cubed because there's something called the Baron-Seeley recursion relation. But put that aside for now. I want to come back to it. And there's a practical motivation for this problem because one of the main bottlenecks in actually doing the calculations that are required for data analysis at the LHC, Anastasia emphasized the polylogarithmic functions, but that's under relatively good control these days. One of the main bottlenecks is manipulating these tree-level amplitudes. It's easy to develop files that are gigabytes or terabytes long that just contain enormous sums of products of rational functions. It's really remarkable how complex these things can get. I'm being slightly misleading here because usually we don't need to know tree-level amplitudes for very large n. Typically, these files become very large because we have large sums of products of many amplitudes with small n. So that's why I say this is a somewhat true but slightly misleading motivation. But nevertheless, the real motivation as a more theoretically minded person is there something we don't really understand fundamentally about these particles? Okay, so comments, because this is a tree-level amplitude, you can add up Feynman diagrams and compute it. Every Feynman diagram has some numerator factors, some denominators, but there are no polylogarithms here. It's just a rational function. And moreover, on basic physical grounds, we know where all the propagators are. We know where all possible denominators are. And here I'm using spinor helicity variables, but if you're not familiar with that, it's no problem. You just you think of all possible propagators that could possibly appear, and you multiply them out. You define a new rescaled amplitude where you include this factor. And this thing is now guaranteed to be a polynomial. Okay, and so now if you have a friend who's a mathematician or a computer scientist, you can start asking them what is the computational complexity of evaluating that polynomial for large n. And you can make it really interesting by saying, let me pretend that all the energies and momenta of my particles are integers, okay? Of course, these are analytic functions, they're polynomials, but if we can understand how they behave for integers, we understand what they are. So you tell your mathematician friend, I have a function that takes 4n integers, those are the energies and momenta of my n scattering particles, and it outputs an integer, namely that scattering amplitude. Now, one of the most popular modern methods for computing these scattering amplitudes is something called the BCFW recursion relation. And it expresses the answer as a sum of a certain number of terms. Now, interestingly, the BCFW recursion relation won't produce for you something that's manifestly an integer. It's the sum of a bunch of terms. Each one is a rational number, but magically they add up to an integer. And we call these extra denominators that appear in the individual pieces, well, they have a physical interpretation as spurious poles. They're basically poles that have to sum basically to zero. They have to cancel out in the full expression. Okay, now if you look at this quantity here, for fixed k, this grows like n to the k, but in the worst case scenario, if you want to take a large number of positive helicity gluons and a large number of negative helicity gluons simultaneously to infinity, that number grows like 4 to the n. Whereas I already told you that we know, based on work from decades ago, that the answer cannot be worse than n cubed. But looks can be very deceiving, right? There's a famous example of a kind of polynomial that has n factorial terms, but only takes complexity n cubed to evaluate. That polynomial is called the determinant. If you write the determinant of a matrix and expand it out, it has n factorial terms. But you can also compute the determinant by diagonalizing the matrix. That has cost complexity n cubed, and then multiplying the eigenvalues. So if you have a random polynomial, it's very complicated to evaluate it. But certain very special polynomials do much better. And one huge open problem in scattering amplitudes, now that I've started phrasing things in this way, is there a formula for the tree-level scattering amplitudes of gluons that is like a determinant, okay? And the fact that we know that it should be no worse than n cubed based on Barron's helix suggests that something like this exists, but it's not known yet. This problem it's basically, well, in sophisticated language, we call the problem of finding the dual amplitudehedron, but that goes far beyond what I wanted to say. All I wanted to emphasize is that these BCFW terms are not random, they're very special. They're doing something very special, and we want to understand that structure better.
Isn't there an this sort of determinant I mean, it has the scale, no?
It has the right scaling, but it's not the case that they write down a matrix and you take the determinant of it. Yeah. It has the right scaling, which is suggestive. Exactly, yeah. So in a paper some time ago, we and some collaborators conjectured, based on some numerical experimentation, that the individual rational functions in these BCFW terms satisfy a notion of cluster adjacency. You already heard about this a little bit in Anastasia's talk, but because I'm talking about tree-level amplitudes, not polylogarithms, it's even simpler what I mean here. So I just remind you that a cluster algebra is generated by sets of variables that are related to each other in a specific way called mutation, these arrows. And this is a new word I'm introducing. Two variables are called compatible if there is some cluster where they live together. And at tree level, cluster adjacency, we have rational functions, so we have a sum of many terms with numerator and denominator. The word cluster adjacency means that the denominator in each individual term is a product of compatible cluster variables. So this is a very special property. This would not happen if you had a random rational function. It's some very specific property, and I'm not making a direct connection between this and the n cubed scaling. I'm just saying this is one of the special mathematical properties that these things have, and we would like to understand more special mathematical properties. So this fact has now been proven by mathematicians, and if you want to have a sophisticated way of saying it, they say that BCFW recursion is a cluster quasi-homomorphism. But okay. In our recent paper, oh, sorry, in that older paper, we worked in the momentum twister variables that you heard summarized. But motivated by recent work exploring the connection between the cluster algebra associated to the partial flag variety, we wanted to revisit the question of cluster adjacency for tree-level amplitudes expressed in the more familiar spinor helicity variables. And here we focused on a certain class of amplitudes called split helicity. That just means that we're at tree level, so all amplitudes have a natural color ordering. So that means that you consider the positive helicity gluons to all be cyclically adjacent and the negative helicity gluons to all be cyclically adjacent. You don't have any no crossings between positive and negative helicity. And what another interesting thing about this specific class of amplitudes is there's an explicit formula for it. It's not the simplest formula, but it's completely explicit. The amplitude is given as a sum over zigzag diagrams. What is a zigzag diagram? You put all of the negative helicity gluon labels on the top, all of the positive helicity gluon labels on the bottom, and then you draw any curve that bounces back and forth. It's not allowed to cross itself. It could go in between or skip any one of these segments. It starts at the top and bounces around. And once you've drawn a curve like that, that means you've chosen certain pairs here. These A1, you could have an A2, you could have many of them, B1, B2. And once you've drawn a curve like that, every factor in this formula is completely determined. And I won't review all the notation, but these are just kinematic variables and spinor helicity variables. So there's an explicit formula for this kind of amplitude, and we want to know is there any special mathematical property here that might give us some hint towards better understanding the amazing structure here. Now, one big difference between the Grassmannian cluster algebra and the flag cluster algebra is that the flag cluster algebra breaks the natural cyclic ordering. So you see here, as I said already, these have a natural cyclic ordering, and that's reflected in the way these are arranged around that oval. But the embedding of the flag cluster algebra into GR4, breaks that. So therefore, you have to allow yourself to consider, in principle, arbitrary permutations of the particles, and which is fine because these are bosons. So the full amplitude is actually fully symmetric under everybody, under arbitrary permutations. So based on, again, on numerical experimentation, that's how we do things in this field. We try to see if something is true. We check it in many examples. We make a guess. We try to prove it or derive some consequences from it. So based on numerical experimentation, we conjectured that the cluster adjacency holds for a very specific set of permutations that you can read off. And here I give an example. This is a zigzag diagram for 17 particles. I haven't closed it at the ends, but there's a zigzag. And if you read from right to left, there's a block here with 3 gluons. So I put aside 1, 2, 3, and now I start reading to the left. The first region I encounter is this region, so I call that 4. The next region I encounter is this region, so I call that 5. The next region I encounter is this large triangle, so I call this 6, 7, 8, 9, 10, 11, 12, 13. Then here I have a region at the boundary at the end again where I leave aside 14, 15, 16, 17. Then there's a certain allowed set of permutations for 1, 2, 3, 14, 15, 16, and 17, according to which this specific term, given by this formula, satisfies cluster adjacency. Okay, so I'm now concluding part 1 of my talk. This is just meant to be an example of the kind of completely hidden physically obscure. We know no physical reason why this should be true, but we're trying to understand what is the mathematical structure of these formulas, and many things to do include trying to prove it, checking cluster structure with respect to different choices of cluster algebra. Yorgos and his collaborators had a different cluster algebra associated to spinor helicity variables in their paper, extended to other helicity amplitudes, or more importantly, understand what this means. And can you use it, for example, to prove the n-cubed scaling someday? Okay, now I'm going to turn to the second part of my talk, which has to do, again, with loop amplitudes, which are, of course, are crucial for precision physics analysis at collider experiments like the LHC. But unfortunately, I'm going to have a long philosophical digression here. So first I'm going to start with the question, what does it mean to evaluate a loop integral? Because we've seen also in the previous talk, but also in Anastasia's talk, these polylogarithm functions and their generalizations. So suppose that you evaluate a Feynman integral, but you express it in terms of special functions, and those special functions are themselves defined by integrals. Have you made any progress, right? If you want to evaluate a function and get some number of digits out of it, you use a computer program like Mathematica. But how does Mathematica get those numbers? Well, it might know the integral definition of cosine or log or Lie2, and it might be numerically doing that integral. So you're kind of like going in circles, right? You're taking something, all you're doing is you're writing an integral in terms of a class of functions that happen to have names because some famous French mathematician in the 1700s defined them and studied them. Okay, so what does it really mean to evaluate a loop integral? Okay, here I already said this. I'm imagining someone who wants to get digits of precision. Okay, so a practically minded person might be happy to say that a loop integral is done if you've reduced it to a form where you either have a convergent power series expansion, because then you can get as many digits of precision as you want if you know the radius of convergence, or you've reduced it to a form where it's an integral of a rational function with as few integrations as possible. Now, what I mean by as few integrations as possible is, generically, if you have a Feynman diagram with L loops in it, you have to integrate over the L different loop parameters. And if I'm working in space-time dimension D, you have to do an integral of this form, where you have some rational function, and then you integrate it over the loop momenta. Now, in practice, in every example that we know of, and this is poorly understood, but roughly half of those integrals always give you factors of pi. And this is what you see, for example, if those of you might know, if you've studied quantum field theory, if you introduce Feynman parameters and then you integrate out the loop momenta, you get representations that look like this, where you have a bunch of factors of pi sitting out front, and then some rational function integrated over the Feynman parameters. So this is what I mean by saying you want to try to get rid of as many integrations as possible. Now, there's a problem. There's no general efficient algorithm for starting with something like this and ending with something like this. People write PhD theses on new methods for evaluating Feynman integrals in their books on it. But even worse, once you've got down to this stage, there's no effective algorithm for determining if two expressions are the same. So if you and your collaborator are trying to evaluate the same Feynman integral, and you use one trick, and your friend uses another trick, you might have some formula, and they might have a different formula. Each one is a gigabyte long. They look nothing like each other, but secretly they're equal to each other, hopefully, or you want to check if they're equal to each other. This is a bit, that's what I just said. Yeah.
So you are saying there is no something like an analog of Poisson also there is summation and things like that. Analog.
Okay, yeah, very roughly speaking, yeah, I guess so, yeah. So one way to state this is that you can have many different ways of writing the same function that differ from each other, either by changes of variables or by integration by parts, basically adding 0 under the integral sign. Now, imagine that there was an algorithm for picking among the infinite many different ways that you could write something, like a specific representative. Let's call it a canonical form. Then you could easily compare whether two things are equal to each other or not. Now, here's where I really get into philosophy and into number theory, really. In number theory, there's a notion of something called a period. The name comes from physics because this has to do with like the period of it. You know that if you have a pendulum of a certain length, it's approximately a harmonic oscillator, but not exactly a harmonic oscillator. And so the period of a pendulum of a certain length is actually an elliptic integral. So it's not a rational number, and it's not even an algebraic number. So here we have natural numbers contained in integers, contained in rational numbers, contained in algebraic numbers, contained in periods, contained in transcendental numbers. So a period is any number that's the volume of some region in Rn that you can describe with polynomial inequalities with rational numbers. So for example, pi is a period because it's the area of a circle. And a circle you can describe as a polynomial with integer coefficients. But the number e, for example, is conjectured not to be a period. So there's no volume in any dimension that's described by rational polynomials whose volume involves e. Okay, so a giant open conjecture in number theory is that if you have two periods that are equal to each other, then there has to be an explanation for it. Like you have to be able to take one of these volumes and cut it up or do some transfer, like a rotation or change of variables to map it to the other volume. In other words, there's no accidents between numbers that are periods. And what we see here is that that's a reflection. It's basically that it's an example of the same phenomenon. So,
just to understand something. So the reason for which the result is period is because of the kinematics constraints.
Right. So it's a general fact that
because of rays of energy, for example, or what?
So the kinds of integrals that come out of any Feynman diagram calculation, like the polylogarithm function, have the mathematical property that, for example, if you choose all your masses and your momenta to be rational numbers, then the answer will always be a period.
Because of rays of energy.
No, just because of the generic ways that Feynman rules look like. They're like polynomials in the numerator and propagators in the denominator. Yeah, this has nothing to do with any symmetry or it's really just the basic structure of quantum field theory.
Is that a perturbative statement?
Yes, it is absolutely. Thank you. It's a perturbative statement because this is at fixed loop order. Okay, now for one very how much time do I have left, by the way? Oh, okay. Okay, maybe I'm rushing a little bit too much. Okay. For one very special class of integrals that happens to be very important in particle physics, this is a class of integrals that belong to generalized polylogarithm functions. There is a tool, there's a powerful mathematical tool that will tell you if two things are equal to each other or not. And that's called the symbol for generalized polylogarithm functions. So if you and your collaborator are doing the same calculation and you happen to be computing something that belongs to the special class of functions called generalized polylogarithms, then it's easy for you to compare. Even if your file is a gigabyte long and their file is a gigabyte long, there's this mathematical machinery called the symbol where you can check each other's work. It's like calculating a hash or just a checksum or something, if you're familiar with those words. Okay, so this was all kind of motivation. We're going to circle back to it in a minute. The curve integral formalism developed by Arkani Hamed and his collaborators is something that applies to any colored theory. And that means that all of the particles are in the adjoint representation of some group. Let's call it UN. We don't necessarily need large N. So this would be applicable, for example, for QCD, even for N equals 3. But it's not yet at the point where we can describe quarks, because quarks are not in the adjoint. We could describe anything in the adjoint. The particles can be massless or massive, and you can work in any space-time dimension D. It's an arbitrary parameter. The idea is that the curve integral formalism, which I'll give a cartoon on in a minute, tells you a combinatorial algorithm for you to write down. You don't need to do any Feynman integrals. You draw some pictures and you write down an expression like this, where you've already sort of minimized the number of integrations, and you get a formula that represents the sum of all L-loop Feynman diagrams. And again, you can do this at the planar level, or you can do this at any order in the 1 over n expansion. And remarkably, the complexity of computing this integrand is order n squared. Compared to if you wanted, for example, if you were working in phi cube theory, if you had Feynman diagrams with vertices that have 3 legs, and you wanted to draw all Feynman diagrams, you would have a computational complexity of order 4 to the n. Whereas in contrast, it only costs order n squared calculations to write this down. And here's how it works, just in a nutshell. Let's say you wanted to calculate a 3-particle scattering amplitude and order 1 over n. That means non-planar, but sort of first genus beyond planar. You draw this red surface, okay? It has 3. It's an open surface, meaning it has a boundary, the red boundary. It has 2 boundaries, one of which is red and one of which is green. So on this red boundary, you've got 2 of your external particles, number 1 and number 2, and they're like holes or punctures in my surface. Then I've got this second piece of surface, the green one. It's non-planar, so a portion of it, like a highway, goes underneath the other portion of it. And it has 1 external particle. I'm sorry you can barely see it there. Number 3, there's a little puncture there. So this represents a collection. This represents it's a topological diagram. So you're computing. What we're trying to compute here is the sum of all Feynman diagrams that have this topology, meaning that they contribute at this loop order to a 3-point amplitude at this order in 1 over n. And the way the curve integral formalism works is that individual diagrams correspond to triangulations of this surface, but we don't need that. We're not interested in that. The curve integral, you can compute it by writing down all of the curves on this surface. So a curve, I've drawn one example in purple. A curve is something that starts at one of the points and ends at another one of the points. It's this purple curve here that goes around. That's not the only one. There are many of them, but that's one of them. And the idea is you look at all possible sets of compatible curves. Compatible means they don't cross each other. And once you do that, there's a very specific formula that you just write down and you get your integrand. So here's an example. This is a simpler example than the one I drew. This is for a 2-point one-loop bubble diagram, say, for example. And there are a number of Feynman diagrams that contribute to this, but you can just write down this formula. So to make a connection between the long motivation that I gave previously, this is something that moves into the direction of being able to write down some kind of canonical representative for the kinds of functions that we see appearing in quantum field theory.
Excuse me, what is T1, T2?
Yeah, thank you. So these are basically Schwinger parameters.
Okay.
They're basically or they're related to Feynman parameters. So graphs with this topology would have two propagators,
Okay.
and so no, but good question. But the point is, you totally skip the step of writing down the Feynman diagrams and doing the loop momentum integrals. The curves directly involve T1 and T2, and there's a formula, you just write it down and you get this.
Okay.
Now there are some things that I haven't, I think I've defined everything here. It's a 2-point amplitude, so you have one particle coming in, one particle coming out. It carries momentum p, so this will be a function of p squared by Lorentz invariance. Capital D is the space-time dimension, which is arbitrary. Right. So Arkani Hamed and collaborators first wrote this down for the simplest colored phi cube theory, a scalar field theory. They generalized it to Yang-Mills theory, non-supersymmetric, in another series of papers. And the fact that D is just an overall parameter has some advantages and some disadvantages. It has an advantage that if you have an amplitude with divergences, whether ultraviolet or infrared divergences, you can use dimensional regularization because D is just a parameter. However, it has a big disadvantage. The fact that D is arbitrary means that you cannot make use of any of the very, very, very special things that we know happens in 4 dimensions. So in 4 space-time dimensions where we live, you can use spinor helicity variables or momentum twister variables that we've heard about that buy you an enormous amount of simplicity. But you can't directly use those here because the formula is equally applicable in any number of space-time dimensions. So for that reason, you know how if you're comparing 2 algorithms and one algorithm you can prove is asymptotically better than another algorithm, but that asymptotically better algorithm has such a large coefficient in front of it that the calculation that you would need to do to see the improvement would be like, a Google particles or something like that. You don't really care. So the connection I'm making here is even if this curve integral formalism is asymptotically better for understanding the kinds of field theories we're interested in, the fact that we can't use some of the machinery that's special to 4 dimensions is really a huge drawback. It means that it will take a long time of people developing or understanding this better before it could even possibly have any potentially practical use, in my personal assessment. Another thing you might worry about this. Oh, yes, of course.
In Feynman integrals, one can always separate out the dimension of the external particles, set it to 4 if one wants, and then the dimension of loop interpretation. For every loop, you can choose different. But this is not possible, I guess, in this curve integral form.
No, I think you can, and the formula becomes slightly more complicated. Right, because this D they've done the step of integrating out the loop momentum for you, and I think you can choose different Ds for each loop if you want. And of course you can, after the fact, you can specify that this lives in 4 dimensions, not in 4 minus 2 epsilon. But you see from the formula, in this formalism, that doesn't buy you anything, right? In other formalisms that we're used to, it helps if you specify the external kinematics are in 4 dimensions or not. Now, another thing that you might find very weird about this formula is that we're not used to seeing integrals in physics with max in them, okay? That's really unusual. The non-analytic integrand may frighten you, but actually there's some really fascinating mathematical progress recently called tropical sampling for numerically evaluating exactly these kinds of integrals. And there's a nice talk about this at Amplitudes 2025. Giulio Salvatore can go up to 14 loop order on his laptop doing these integrals numerically. And actually Berinsky himself recently published a paper where he computed certain contributions to the beta function of phi to the 4th theory up to 50 loop order, just as a proof of principle, using this tropical sampling techniques. As the word sampling implies, it's like a Monte Carlo way of numerically calculating these integrals, but it knows exactly which regions of the integral contribute the most, so it can focus all of its effort in those areas, and you get extremely fast convergence. Okay, so in my last few minutes, what have we done after this very long philosophical introduction? Well, if you want to get anywhere close to the real world, you need not just scalar particles, not just gluons, but one thing you need is fermions. So we worked out how to generalize the curve integral formalism to include colored fermions, so fermions in the adjoint. That's not quite quarks yet, because quarks are in fundamental and anti-fundamental, but at least we have fermions. That's the first step. Fermions with Yukawa interactions. And what you need to do is you need to generalize your curves and surfaces so that you can allow surfaces that have either bosonic or fermionic boundary components. It's natural to think of these surfaces as living in superspace, but let me not emphasize that. So here's an example of a contribution to a 2-point amplitude psi bar, and so there's a natural way to generalize this, and you can assign to each curve on the surface, you have either bosonic curves or fermionic curves, and in an L loop amplitude you have to sum over 2 to the L possible assignments of the curve that goes around its puncture. So here's an example of a curve that goes around some puncture without going between the internal and external particles, and that can be either bosonic or fermionic. If you're a string theorist, this is kind of smells like summing over the 2 to the L or 2 to the G different spin structures if you're doing string theory on a genus G Riemann surface. And then, oh, I think I skipped one. Oh, yeah, here it is. And then we write down a specific formula for how to compute this amplitude by evaluating certain simple determinants. Okay, so to summarize, because I see the chair reaching for the paper, yeah. Dramatic progress has been made in recent decades, but many fundamental questions about the structure of quantum field theory remain unsolved. Seeking new formalisms may help to shed light on some of these questions, and I focused on that in my talk because Anastasia focused more on all the things that we do that are actually potentially useful. So with that, thank you and Merry Christmas.
And for a crystal clear talk, so you mentioned the
tell us, like, has this actually been applied? Like,
Yeah, no, those are two separate things. Because the symbol is very special for multi-loop amplitudes that evaluate the generalized polylogarithm functions. Whereas in the curve integral formalism, usually it ends up giving you something that can be numerically evaluated. So you don't know, is it polylog or not?
But somebody could say, like, the motivation for the symbol was that we can relate different ways of valuing. And this is a canonical form. So one could go back and see.
Maybe, yeah. So exactly. So the transition there was a little rough, but maybe the curve integral gives you something like a canonical form that's more general than the symbol. That's the idea.
Okay, so now it's the end of this conference. So the organizers asked me to say some words. I have prepared something. It's not long, don't worry. I'm not going to say a lot of things. But the organizers asked me to say a few words since this year, as you very well know, marks the 10th anniversary of the workshop that we have started some months ago. Anniversaries are the ideal time to reflect on how we started and what we have accomplished. The conference began in 2014, in the middle of the financial crisis. The situation in the country and in the universities was very different from the situation that we have right now. Reduced salaries, non-existent scholarships, brain drain, and faculty members could maybe travel abroad, but for the students that was different. So our primary goal when we started this idea was to connect the Greek scientific community of the diaspora with the scientific community here in Greece. The money we received initially from the university was not enough to invite speakers from abroad, and we could only pay for the dinner that it is offered at the end of the conference. However, besides the financial crisis, we counted on the people's sincere willingness to support this initiative that we started. And we were correct. We never got a negative answer, at least for the period that I was in the organizing committee, from someone who was coming to Athens for the Christmas holidays about also attending the conference and contributing with a talk. Of course, over the years, the situation improved. And now the conference gets better and better every year. More speakers, more participants, and some funding provided to the organizers in order to improve clearly the quality of the conference. 3 days of very interesting talks on diverse topics. But what is more important is that this conference has created a tradition that was absent before. Every year, you can see from the webpage that more than 100 people enroll as participants, and very rarely you will find fewer than 50 people inside the amphitheater. Faculty members, postdocs, PhD students, even undergraduate students are coming to attend this workshop. That means that it is already an established scientific event of our community, not only within Greece, but internationally. 10 years was just the warm-up. The next 10 years will be even better. So, having said that, I would like to ask all of you to give the organizers our warmest applause. Thank you very much.
Do you mind if I say a few more things adding to what Dimitris has said? I couldn't say it better, but I would like to emphasize that the University of Athens continually supported financially this event. This year we also had 2 publishing companies, Utopia Publishing Company and Gutenberg Publishing Company, as well as with the World Scientific, who is going to publish for free the proceedings of this conference, marking precisely the 10th anniversary. Okay, I have nothing more to say. I hope the next 10 years will be even better. And I will take also the opportunity to mention that some of you might be interested in coming back to Greece, to Athens, at the beginning of May, because we are organizing the Eurospring 26. Thank you.
From the speakers and participants, of course, it's your participation that makes it so special. Merry Christmas and see you again next
Fiscal